So, good morning. I'd like to welcome you to the ML Workshop 2024. We have two talks for this first session. If we can welcome Guillaume Munch-Maccagnoni, who's going to talk on designing interrupts for ML and OCaml, looking for a sound design for asynchronous exceptions. Thank you, Guillaume.
Hello, everyone. The topic of this talk, that's what happens when you press Ctrl-C on your keyboard because you're fed up with what the program is doing. Oh, thank you very much. Okay, so you press Ctrl-C, and your program has to react to it. And most often, you want it to continue. You interrupt what you were doing, but you want the program to keep being responsive after that. So that's a classic problem. When we are talking about ML, we are talking about programs that may contain state, so local and global state. What happens if you interrupt and your data structure becomes in an invalid state? So a while ago, upon rumors hearing that OCaml developers wanted to remove asynchronous exceptions from the language, or at least make them more marginal, so I surveyed the use of asynchronous exceptions or interrupts in the OCaml ecosystem. So I came up with a list of packages that depended on this feature. And there are quite many uses of that. There are some high-profile programs in there, programs written by impressive people. And what you find is that tools like proof assistance, compiler, interactive language tools, or CLIs, they do rely on this feature. And what they do is they want to react to signals like SIGINT or SIGAlarm, SIGTERM, or even SIGPipe. I saw that. They want to check regularly if some memory limit has been reached and interrupt the program if it's too high. What they want to do with it is they want to put a specific message for what happened upon this interruption, or they want a specific user interaction, or they even program a distinct behavior, distinguishing what happens upon a voluntary interrupt and a crash, and we take a different course of action. And in the OCaml world, you can even have errors that arise from your finalizers. I'm not saying that it's a good thing, but it's the situation, and we want to work towards making the situation a bit saner. So there are further motivations, which is to go towards having a notion of cancellation in the asynchronous, green thread frameworks. This corresponds to the idea that when you move your scheduler into your program and you write your own scheduler, then you're moving part of the OS into the programming language. So how far do you have to go? Maybe you have to move isolation features from the OS into the programming language. And what's behind this notion of interruption is also a non-defensive model for reacting to errors. So that's related to the philosophy of Erlang, of when you've got an error, the best way to write your program reliably is to fail as quickly as possible, and let the failure percolate to the person who can really react to it. So the point we are making here is that so there is an exception handling model that has been brought forward by the Rust language, which is an evolution of the C++ error handling model. And the claim is that it can be extended to deal with asynchronous exceptions or interrupts. So there are various challenges with interrupts. In ML, they are implemented as exception arising out of thin air. So any code location can raise an exception. It's obviously a challenge for reasoning about stateful program. So when I catch the exception, is the state of my program still in a valid shape? Then when you get into the details, you find issues where maybe before catching my exception, some other exception happened. So now I have multiple exceptions in flight at the same time. So how can we make sense of that? So another challenge is that OCaml has evolved towards systems programming recently. So there's a whole bunch of programs that expect no asynchronous exceptions at all, and that are written with this assumption in mind. Moreover, so the OCaml multi-core project was designed at first around this specific dialect of OCaml. For instance, the notion of fiber in OCaml, there are resources that you need to drop explicitly. So either you use it or you drop it explicitly. You must not let it fall on the ground. So if you have an exception arising in the middle of nowhere, then you don't know what to do. On top of that, we don't want to force programmers to code defensively against exceptions. We don't want to force programmers to apply the program-wide discipline. As we will see, that's a solution that's currently in use to make sense of those interrupts in the ML ecosystem. So, reviewed the current approaches. So, proof assistants like Coq and Isabelle tell you that there are critical exceptions, and you must not catch them. You must let them terminate the exception quickly. So they apply a program-wide discipline that programmers must follow. There's a distinction at runtime between critical exceptions and other exceptions. And when you write a catch-all, you must by hand make sure that your exception is not critical. On to managing state. There are various kinds of state. The first one is the notion of resource. So we take the good advice from Haskell of having a combinator that deals with all the subtleties of the races that can happen between resource acquisition, resource release, and asynchronous exceptions that might happen. And there's a good reference on this topic. Michael Snowman wrote a blog post on this topic. And already here, if you read the blog post, actually you can see behind it something similar to the C++ approach to exception safety. Now, what about non-local states? So something clever in the Coq proof assistant is that there are some stateful computation, but upon an interrupt, it will roll back to the previously known good value. Another thing you can do is to invalidate the state to propagate the information of the failure to other users of the same non-local state. Now, what about if there is some local state? If there is some local state, it will disappear with the part of the program that you're going to interrupt. So it's not an issue in general. And what the Rust programming language came up with is a trait called unwind safe that labels your data structures by telling whether you can recover from an interrupt or not. That means when you are catching an exception in Rust, so you pass your closure to the catching combinator, and the type of this combinator checks that everything inside the closure actually survives this interrupt. So you are forced to explicitly say that you have no local state when you catch an exception. Now, all these approaches, I want to rephrase them, and I want to start from the beginning. It's the difference between the, errors and exceptions. So errors, such as result types or catchable exceptions used for control flow or simply reporting errors that can be handled by the caller. So they must be handled by the caller. And this should be distinguished from the notion of exception, sometimes called serious exceptions, which must be handled only at appropriate isolation boundaries, because it's the role of the person catching the exception to make sure that no invalid state can escape from the part that has just been interrupted. So here, for ML, the term exception is overloaded because if they are catchable and serious exceptions, we want to make the distinction. So Rust has the term panic for that, and it comes with features to ensure isolation. So the distinction, so when we say serious, critical, and all that, we think about a value judgment about what my error is actually. So I don't care about that because I don't know how to program with that in mind. What I need is that I have different facilities in the programming language that are adapted to different ways to structure and reason about the program. And the distinction here is who is responsible for ensuring the consistency of the state. Is it the caller, or is it the person who's going to catch the exception? So we can easily outline an approach in ML to make sense of interrupts. This is a bit what happened in the Isabelle proof assistant. You don't have catch-alls. All exceptions are considered as serious. And you need catch-alls to do things like resource management. So instead of doing it by hand, you will be given appropriate language features to do so. So in the end, you get a model where when you program, you don't have to think about whether there is an asynchronous exception that might arise or not. This is not your concern. It's the concern of the person who's going to catch this asynchronous exception. So when you write a task, it has to be written like any program. All you have to do is to fail fast in the event of a failure. And you have to use the provided resource management features to manage your resources. But the catcher must make sure not to share state, its personalized state with the task, unless this state is protected. And once you take this approach, and when it's done right, then there is no possible interrupt happening between raising an interrupt and handling this interrupt. This means that we also get rid of the problem of having multiple exceptions in flight. So when you get into the details of an established language like OCaml with specific constraints like backwards compatibility, it becomes a bit more complicated. So I guess I'll go quickly over those slides. There are lots of details, so maybe I don't have the time to explain it all. We have a list of requirements for having interrupts in OCaml and making the situation better. The first one is that interrupts need to remain opt-in for backwards compatibility reasons. There are some asynchronous events that we don't want to delay, for instance, related to memory profiling. And we want to make it impossible to confuse catchable and serious exceptions. For instance, we don't want someone to be able to raise not found in the middle of nowhere. We want to make it possible to enable certain code transformation for optimization purposes. So we want to get rid of the hypothesis baked inside the compilers that every allocation points may raise an exception. So the proposal is to add a new kind of exception besides the exceptions that currently exist, that are distinct from other OCaml exceptions, and that are not caught by catch-all handlers. We don't provide a catch-all for those exceptions. Instead, we provide the suitable resource management features. Another part of the proposal is that we want to distinguish asynchronous events depending on whether they are raising or non-raising. That means that there are some asynchronous events that are run promptly but cannot raise an interrupt, and some that can be delayed, but then that are allowed to raise an interrupt. And with more constraints come more guarantee. It actually becomes useful to have this notion of non-raising callbacks because it guarantees you that you are on the exact fiber that provoked this asynchronous event. So there are various details to make things right, and there are things that are that become a bit complicated and require a bit of work. First, what happens with system calls that may receive eintar, and what happens with standard library globals? Are they interrupt safe yet? So this has to be audited and fixed. And there are reflections about backwards compatibility. So to conclude, some work has been done, like implementing a notion of masking to delay asynchronous events so that I don't have interrupts in the middle of paths where I don't expect them, for instance, resource management, so that we can implement some resource management combinators. So there was a prototype of that written 5 years ago, and that needs to be updated. There's work done to see how it could be to not have asynchronous exceptions in f-lambda2, and that not only enables code optimizations that would not be possible before, but it's actually required for correctness of the f-lambda2 compiler. And so our work with Leo White and Steven Dolan is to reconcile all these different trends and different ways of using the OCaml language. So as a perspective in OCaml, we want exceptions to either become panics or checked exceptions. So we want there to be an evolution path towards a saner use of exceptions. of course, for backwards compatibility reasons, the currently notion of exception might remain for a long time. And finally, what this illustrates, this whole talk, is that structured programming is an ongoing research paradigm. That means I have features that sometimes do not let me express what I want to reason about. So that's the case for GoTos that were replaced with more structured facilities. And when you think about exceptions, it's a bit the same. So what am I really doing when I am programming with exceptions? So I'm not using the whole facility. I'm using some well-designed, some parts of it in a well-designed way that lets me reason about it. And we want to put that structure directly into the language. And finally, when studying that, we found this unwind safe trait in Rust that lets you say whether you can survive an interrupt or not. That has some kind of model character that I invite the community to study because it looks quite interesting. Thank you.
Thank you, Guillaume. We have time for some questions. If people would like to come up to the microphone, forgiving them is probably easiest at the front. If there are any questions. In which case, I have a question. You said the prototype implementation is roughly 5 years old, so presumably that predates multi-core OCaml, therefore. Is there anything that you've looked into in terms of interrupts specifically, so things like Control-C handling, for whether there's an elegant way of doing that using effects? Whether there's a way of doing that using an effect instead of asynchronous exceptions. So effectively to allow a domain to unexpectedly perform an asynchronous effect, but that might allow resumption of it. Is that something that's been looked at?
So the question is, can I do something more than raise an exception during the asynchronous events, and can I perform effects? So that's related to a notion of asynchronous effects that has been studied by, oh yes, Daniel Amann, yeah. And Mathieu Preta, thank you. So they have this notion, presumably, you could extend all that not just to asynchronous exceptions, but asynchronous effects that would be performed inside the asynchronous callbacks. So there's a lot of hurdles to implement that in OCaml for very low-level questions. Mainly, so there are two questions. First, it's currently implemented in C. So you'd have to capture the C stack, which is something that the OCaml compiler does not know how to do. And it's not just a technical problem. It's, if you think what happens if you're currently in some interoperability between C and OCaml and you have a callback from OCaml to C, you have the same issue. What happens if your asynchronous effects just happens while you are inside your callback, while you are in C? And so there are challenges. So maybe it's desirable, but it's a lot of work.
So, kind of connected to that question, have you thought about handling incoming asynchronous effects in JavaScript? So imagine running your application in a web browser. Does that change anything? I mean, will this work in WASM JS of OCaml?
So I'm not familiar with the way those are implemented in JS of OCaml, to be honest. The outline we gave are on the language side, but I expect to be dirty details when you look under the hood.
So I'm sort of specifically thinking, I don't know, if I just get some sort of signal, I press a button or something. Should I see that as a kind of panic or something else? Or does that require some more general notion of asynchronous effect?
Well, it depends what you want your button to do. If it's a button that needs to interrupt what you're doing, then you need something like that to hook your JavaScript event into some kind of asynchronous signal. So here, we just want to handle the way you can interrupt your stuff. We are not looking to do anything more fancy. So maybe
I guess closing your browser window, would that just turn into some other kind of panic?
I'm sorry, can you repeat?
If you have a web application, you close the window.
Mm-hmm.
Is that more analogous to the kind of thing you're...
Yeah, that's very analogous to the applications that use SIGTERM. Yeah.
Thank you.
Thank you. I think if we can thank Guillaume one more time. So next we have a talk on Fram, a new language aiming to increase the ergonomics of algebraic effect handlers. And over to Piotr. Once the screen's ready.
Okay, so thank you for your introduction. This is joint work with Patricia Balik. Patricia is there. I will start with something completely different. So in 1879, USS Jeannette sailed through the Bering Strait and got stuck in the ice. And after almost 2 years of random drifting, the ship was crushed by the pressure of ice and finally sank. But the remains of the ship were found near the Greenland, so this inspired Nansen to organize a journey to the North Pole. His idea was quite simple: just get stuck in the ice and wait. But he needed a ship that would withstand the high pressure of ice. So they built a ship called Fram. Fram in Norwegian means forward, and they tried to reach the North Pole. However, they didn't manage to, because the random drifting of ice, they go in wrong direction. However, the ship was used in another polar expedition, in the well-known Amundsen expedition to the South Pole. So we decided to name our programming language after that ship. And our initial goal was to improve ergonomics of programming with algebraic effects and especially lexically scoped effect handlers. However, we tried to experimenting with some implicit parameters, and we started to generalize this mechanism, and we finally realized that it's quite interesting thing, which is not related to algebraic effects. So today I will say absolutely nothing about algebraic effects. So, let's start with the beginning. Fram is designed in the tradition of ML, so like many other ML programming languages, its type system is stratified between types and type schemes. The idea is that types describes expressions and type schemes are polymorphic, but they can describe only variables. So each time when we use a variable, it must be immediately instantiated with some types. So this is not the full system F, it's just something weaker, but still is very expressive and have decidable type inference. And this stratification allows for many useful extensions. For instance, we have rank and types. In rank and types, we observe that parameters of functions are usually bound by variables. Variables can be polymorphic, so functions can take polymorphic arguments. Another well-known extension is known from Haskell. We can have type classes. We just introduce a new construct to the type schemes and the class constraints. So each time when we use a variable, we have to find appropriate class constraints, or at least propagate them to the place where it can be abstracted. In Fram, we followed this approach, and the grammar of types look like this. We have types, type schemes. Types are just arrows, effectful arrows, and other things. And schemes have very uniform shape. Schemes abstract over some named parameters, and these named parameters can be just types, anonymous types, or named types, or named parameters, or optional parameters, implicit parameters, and some other things that I will not talk about today. For type parameters, when we write an identity function, it's a well-known polymorphic functions. It's in Fram, its type or type schemes looks like this. It's just a function which takes some anonymous type and some value of this type and return its value, this value. So we can write identity function like this. It's the same as in OCaml. We can write it like this. So we can explicitly abstract over these anonymous types. And it behaves exactly like locally abstract types in OCaml. It's just, we name the type which is named locally, but on the outside it's still anonymous. But we can use named types here. And the difference is that this type now is named. The name is part of its scheme, type scheme, so we can explicitly instantiate such a function. We can call ID3 and say, okay, I'm using ID3 with type t equal to int. So we obtain an identity function on integers. And now implicit parameters. So our original motivation was something like this. Let's assume that we want to compute something. And it's a quite big computation, so we need to compute this and compute that. And so we have a lot of code that do something. And now we want to change it. We want to add some logging. So we create some capability of logging, some object that will be used for logging for logging to file, and we need to pass somehow this object to the place where it's used. The obvious way to do that is just to pass it as another parameter to each functions, but it's a very bad design. We need to pollute the code with some boring parameter passing. So we followed the approach to implicit parameters by Lewis and others, where we can we have a separate namespace for implicit parameters, and each time where function expects such implicit parameters, we are looking for such a parameter in the environment, resolving it by name. So now we don't need to pass it explicitly, but still we bound it explicitly in functions. Such implicit parameters are implemented in Haskell, and in Haskell they also are abstracted implicitly, the same as class constraints, but such a design is good for Haskell, where programmers usually write type annotations for functions, for top-level functions, and in each function they say explicitly which implicit parameters they expect. So, but if we only rely on the type inference, it's very error-prone. When we do some typo in the name, then we got an error, and it's hard to figure out from where this error comes from. So we observed that definitions that share some implicit parameters usually come in some groups. So we, inspired by Coq, the section mechanism in Coq, we introduce a new construct called implicit. It's like variable in Coq. We say, okay, we will use this log implicit parameter in the following functions, and each time when it's used, it means that this function must abstract this implicit parameters. So now, values, function that takes values, implicit parameters are values, now are part of the scheme. Schemes can abstract over some values, and these values can be instantiated explicitly. We can say, okay, we can compute that function from the previous slides, saying, I will use the standard error for logging. Or we can omit this parameter, and then it's resolved by name. But we can have different policies for resolving such omitted named parameters for different kinds of named parameters. We can have optional parameters, and when it's omitted, then we take some default values. We can have usual named parameters, which cannot be omitted. So everything now is very simple. There are very simple ideas. So now we will do the complex things using very simple methods. Usually we do the opposite direction. So let's start with records. In many programming languages, we have special kind of data types called records, and records are just tuples where components are named. In Fram, we have no records. Records are just syntactic sugar. So such a definition in Fram is desugared for that. It's an algebraic data type with single constructor with the same name as the type. And this constructor, it's polymorphic. It's polymorphic in these named parameters, because these named parameters are part of the type scheme. So we say it's polymorphic. And also, Fram, for such records, generates some methods that allows to access each field of this record. So with this definition, so we just write the line as on the top of the slide. It's desugared to these 3 lines, and now we can write code like this. Just, okay, let's compute a sum of two records, 2 vectors. So we create new vectors and can access each component just by saying .x, .y, and everything is for free. Another thing, existential types. So let's start with this simple example. Here we have church encoding of streams. So what's the stream? Stream has some existential type called st here, which represents some hidden state of the stream. We have the current state and a function that produces next state and the next element. So we can iterate this function to produce other elements of the stream. So let's try to write some code that operates on stream. So we will write map I function, which is usual map function, where this parameter f is a function that takes not only element but its index in the stream. So this function, so we need to produce a new stream. So the new stream will be a stream. The current state now can be different. Its stream contains some abstract type, so we can choose type that we will use. So we will use a pair of current index and the state of the current state from the previous stream. And we have this function that produces next state and next element, which is quite obvious. But now, if we want to explicitly say that this new stream, this abstract type st in this new stream is a pair, we can write like this, of course. But how to access, what we should write in the place of this underscore? For this underscore, we need to write a type st from the input stream. I don't know how to do that in OCaml, but in Fram, because this parameter is named, I can explicitly bound it here. Okay, and another example, functors, the module functors. Here we have some code in OCaml. The keywords are orange, so it must be an OCaml. And here we have maps, finite maps. So we have some signature which contains key, some abstract type t, empty map, adding new element to map, finding element in map. And having such a signature, we can write a functor make. I only put a signature of this functor here, which takes keys. Keys are just type with comparator. And we produce a map where this type key is the key that we taken as a parameter. And we can call this functor just providing some module. So let's try to rewrite this code into Fram without using modules. Or we have modules, but we have no module functors. So let's try to write it. First, the module signature can be just a algebraic data type, which have several named parameters. The only constructor map have several named parameters. It has some existential type t and empty map, adding, finding, and other operators. So what's a module functor? It's a just usual function which takes type with comparator and returns a map, element of that input stream. So far, everything is quite simple. We can do the same things in OCaml, and it's a well-known translation of generative functors to some simpler system. But what we should do with this module application in Fram, we can call this function make and saying, OK, let's take every named parameter that this function expects from the module int, just by resolving it by names. So if module int contains such comparator, then we will provide it to function make. And we can do the same with the result of function make. We can pattern match on this map type, and say, okay, let's bind every named parameter of that constructor to the new module or namespace called intMap. So it looks like generative functors, but we don't need functors in our language. So to summarize, we developed Fram, and what's interesting in this language is that we developed it together with students. We use it in teaching. So we have classes where students talk about the design of the language. They implement something in the type checker or interpreter of that language. So it's quite interesting experience for us because they ask very rookie questions, they have different view, they know some other programming languages, and maybe they are not very fluent in the functional programming. So we got interesting feedback from casual users. The Fram is developed together with its theory. The core features of the Fram we already formalized in Coq. So we have logical relations for effect capabilities, the effect system that we have in Fram. Patricia talked about it on Hope workshop on Monday. We also have a proof of coherence of our implicit parameters mechanism. And it's still work in progress and some experiment, but we obtained such interesting thing. It's a very simple, uniform language where it's quite expressive. We can express very complex features known from other programming languages using very simple tools. And we still work on improving ergonomics on programming with algebraic effects, but it's still work in progress. We still change the effect system a little bit, so we will see where we will go. So thank you for your attention.
Thank you, Piotr. Do we have any questions?
I think there was some sneaky stuff going on. So the module encoding was relying on the fact that T is a type constructor, not a type.
You mean you are asking for modules, yes?
Yeah.
And
so go back to the slide. Yeah, so look at that first occurrence of T. Oh,
here. Yeah.
So there's some dependency, right, between the things in the set, right? Because you name T first and then you use it later within the same recursive bindings, and also it's higher. Oh, maybe it isn't, is it? Yeah, it's T applied to val, right?
Yeah, T applied to val. The T is of higher kind. It's
Okay.
from type to type.
Okay, so it's more than just
Yeah.
ML. Okay, fine.
Can you say something about the effect types? Is this on? Now it's on. Can you say something about the effect type system?
So we have how to say it? Okay, we have lexically scoped effects. So and based on effect capabilities. So each handler provides some value that can do effects. And each time when we call a handler, a new fresh effect is created. So we can track it that it will never escape, that effects will never escape their scope. And so the effects cannot be parameterized, right? They are just fresh effect variables. So it simplifies a lot in type inference. And I don't know what you want to hear about.
So is it based on some kind of row typing system, or is it more just sets of effects? I mean, what does it? I guess
Currently,
maybe I should take it offline,
it's a very good question. Currently, we have rows, but we are going to change them to sets.
Okay,
We have some ideas how to do that, but it's still not implemented.
thank you.
We can thank Piotr one more time. End of this first session a little bit early. See you again at, I think, 11 o'clock for session 2. Thank you.
Hello, everyone. So I see that the room is packed, so I hope I did not get your expectations too high. It's just a talk I prepared at the last minute because so there's a lot of hype about linear types. Some of you may have seen yesterday's talk at ICFP about putting linear types into OCaml. So this talk is inspired by reading that paper and more importantly, the papers that it referenced. So as a heads up, my talk is not about yesterday's talk. Just so that it is clear, it's about other works that came before it. So I am, at the start, I'm more of a proof theorist working in linear logic. And so more recently, I studied notions of ownership in programming languages. So I wanted to share my reaction to reading some linear types paper and some observations. So recent linear types paper, I noticed that they differ a lot to theoretical grounding by making allusions to linear logic. And at the same time, they made claims about practicality by making allusions to the Rust programming language. So what I want to share in my talk is my view about articulations between theory and practice. So I have the impression that there is some gap between the modern view on linear logic and linear types. And a last question is, so many of us want to see an analogy between Rust and linear types. And is this analogy justified? Is there any connection with linear logic? So for people who are not familiar with linear types made a lot of promises. You'll be able to do functional programming without a GC. You'll be able to manage resources safely. You will be able to do functional programming with in-place updates, so not doing any allocations. You will be able to program for parallelism without data races. And all of that, seen a bit more abstractly, is the promise that linear types is the key to encapsulating state, non-local state, shared state, and so on. So it's a promise to reconcile imperative and functional programming. So that's quite a huge promise. And it also sounds a lot like Rust, indeed, in terms of promises. So when JR wrote the linear logic paper, immediately a lot of people saw the importance of that for programming, starting with Yves Lafont, for instance, who explained how to how a linear logic-based programming language would eliminate the need for garbage collection. And the history of that is that people realized that it's too limited in expressiveness. And from the 90s, people were looking for ways of increasing this expressiveness. And this history goes not just through functional programming, but the idea was taken also in systems programming and object-oriented programming. So there are lots of work beyond what you find about linear types. So ownership types, uniqueness types, and many things. And so where are we at now? So on the other hand, on the theoretical side, linear logic is a logic. So what's interesting is that it prevents you from forgetting a hypothesis or duplicating it. So the analogy that interested people is to link that with the use of values. And it also has, and that's the important part, modalities that allow you to recover more traditional features, like being able to duplicate either the values or the continuation and so on. Things did not stop with the initial release of Gerard's paper. There are a lot of work also in theory to understand what linear logic is. And it was well the work of 20 years to rephrase linear logic in a modern way. So the first paper, linear logic. I also put here the later paper, which is more textbook style about the modern view. And there are the contents, you can look at them, they are very different. And it took quite a while to go from one to the other. And so to get more into the details, what happened is that there has been a shift in point of view. Instead of seeing linear logic as a logic with modalities, we saw it as logic that say how to relate worlds of different colors. So instead of having one color and a modality that encodes well, what's missing, you have bridges between world, say restricted, non-restricted. And what matters is how these worlds interact. So that's the modern view, shifting from a modality to multicolored logic. So in more technical terms, I go from a commonad to an adjunction, and with specific properties. And what's interesting is what are those properties. So one point I want to try to make in this talk is that the map is not the territory. So the rules of logic, the rules of linear logic, that's not the same as linear logic. So not only there can be different presentations, but it's not just because you read the rules of linear logic that you understand what's going on in the mathematics. So linear logic was invented with certain models in mind. And among the successes of linear logic, there's a certain view about strictness and the links between callback value, callback name, and so on. So when we speak of linearity, whether I use something once or more or not, it's useful to think differently about the linearity of values and linearity of computations. So the notion of linearity of computation, if you unfold what that means in linear logic, say if consuming a pair once is the same as consuming each component once, and so on, actually you see that you are reinventing strictness and strict data types. And if you end up in a logic where you can talk about linear values, then you are already strict in some sense. So strictness is a condition of possibility of linearity of values. So I thought about this shift in perspective, and it makes us see the logic very differently from what it was in the start. At the start, you had modalities, and And at the end, you focus on what is the modal character of each type in link with the modalities. For instance, if you have a pair, is it copyable? Well, linear logic says that a pair of two things that are copyable is copyable. And so the thing with polarities, which embodies this change of perspective, is to bake this structure into the system that I'm studying. And then the modern view also tells you that what matters are the different ways of converting between polarities. And the important example are the functions. Is a function copyable? It depends whether the variables it closes over are copyable. And so that gives you, from the start, the fact that there are several types of closures, depending on whether it closes over linear things or not. And so we can compare what was the first view of linear logic, where you had an intuitionistic arrow, a linear arrow, that gets merged into a single arrow whose intuitionistic or linear character in the early sense depends on the copyable character or not of its argument. So we get rid of this distinction when we use polarities. And instead, we see appear another distinction, a distinction between linear and copyable functions, actually linear and copyable closures. So I like to see linear logic as the sidekick of the theory of effects. So there are lots of interactions between the theory of effects and linear logic. So this explanation of strictness and all that actually can be related to considerations in the theory of effects, monads, and so on. Personally, when I talk about linear logic, I don't make the difference with, I don't put it aside from the rest of the theory of effects. To me, it's supposed to be, I hope that at some point there will be a coherent whole that let us speak about both linearity and effects. And in this theory of effects, there has been a success in talking about the theory of computations, continuations, linear, nonlinear, and so on. And it helped making the link between with sequent calculus and focusing. So I think there was a talk about sequent calculus, and it's interesting to see that the history of those systems actually come directly from linear logic. Okay, so if you want to make the connection tighter, you have to talk about Kolbe-Puchulu and so on. And so I want to talk about different case studies. One work that I like a lot is the work of Jesse Toff and Ricardo Pucella about affine practical types. And they observed that systems that take inspiration from linear logic are either foundational calculi close to linear logic or special purpose type system. And their ambition is to have a system that is both practically minded and close to linear logic. So that was an experiment in language design. And we find that they make the same shift in perspective. So they bring practical arguments for this shift in perspective. So this distinction has a long history, so they did not invent it, but they made good contributions about it. For instance, there are contributions of saying, how do you type a composition operator a single composition operator for the whole multicolored logic, I think it's an interesting contribution also from a purely theoretical perspective. That's a very natural question that we may have. They also emphasize the role of abstract data types, linear abstract data types, to generate new interesting linear behaviors. And it has been criticized because it's, it has some limited expressiveness. That's a valid criticism. So to express certain patterns, you're forced to do some threading of capabilities by hand. So it's less expressive than certain ownership or capability-based systems. And criticized because it's complex to implement, but there have been works to simplify the implementation of that kind of system. And it's also sometimes, and that's the part that interests me here, is that it's dismissed as too complicated as a type system. And the getting from grandpa linear logic to this view of linear logic, of linear types, has been qualified as a swamp. But my view is that it's interesting to see that a practical experiment matches the modern view on linear logic. And that gets me back to my remark about the difference between the map and the territory that I made earlier. That is not because you implement the rules of linear logic that you implement its interesting features. Are you not just forcing the users to do the job of the compiler, for instance? And the last thing that I find a good argument for it is that although it has a bit of a computationally simple interpretation of what polarities mean, it can be generalized to more interesting models of computation. And some aspects remind us of Rust, indeed. So first, the general organization around copyable and affine kinds, which remind of the distinction between the drop and the copy traits in Rust, for instance. It's interesting to see that Rust came with that, not by reading linear types paper, but it came straight from C++ and move semantics that were developed in the early 2000s. And the peculiarity of having several types of closure is very natural in Rust. And the analogy can be explained by link between polarities and type classes for implementing substructural types. Another example I wanted to study is what happens when you want to mix linearity and control. So it's a non-issue. Well, if you do a control effects, like raising an exception or returning, then you are silently discarding variables in the scope. So that seems to go against linearity. And so in ALMS, they were upfront about it. We cannot solve it, so we are going to go with affine types instead. That's not entirely satisfactory because we want to also to control where things are dropped when we want to manage resources, for instance. So it's a well-known issue also in theory because you can state it as the fact that the linear error monad does not have a strength. So I found that other works simply remain silent about the issue. And I'm not sure what is the message. Like, do we want to get rid of exception? Maybe we want some very explicit language in C style. And so I wanted to propose a thought experiment. What happens in practice? If you don't have exception, then you have to use the error type. So when you take something, you have to replace it with something else. And so what happened? Then you're having an error monad that is not strong, that I cannot use. At every place where you want to drop a variable, then you want to be explicit about what happened. And it becomes very verbose. And so the practical experiment about that, you can read papers about Cyclone, and they mention that this is too complicated, and instead they use some fallback deallocation. And what about the very, very explicit C style? Well, actually, that's the part where in C, people use gotos. So you need to have gotos in your language now. We can push the thought experiment further and wondering if the C++ Rust notion of destructor could have been rediscovered with linear types. The idea is that to make the error type a monad, I want to have a canonical way to drop each element. And this canonical way is called destructor. So that's the starting point. But then what happens? Then you're starting to talk about an algebra for this notion of destructor. When you make a pair of two things that are destructible, then you want to say that there is a canonical destructor that's going to drop one, then the other. Actually, if you do that, you start getting at where C++ and Rust is now, and the notion of destructor has been invented for that in the 80s. Another thing is that this is not what we see in works on linear types. So I don't know. So maybe not enough programs have been written in those linear type systems. One last case study that I wanted to mention is the hypothesis that two notions are fundamentally distinct, linearity and uniqueness. And one says that this pointer will not be shared, and that's important if it's a resource that I'm responsible for cleaning up. And uniqueness says this pointer has not been shared. That means that I can reuse the memory. So is it worth it to introduce such a distinction? So it is claimed as a theoretical fact. And I wanted to enter more into the details of the argument. One argument says that a system based upon linear logic cannot guarantee uniqueness of reference. And I found that this depended on the non-standard and computationally, well, trivial to some degree interpretation of Bang. That this argument does not hold in regular models of linear logic. So it, I can make the point in more detail. It has to do with what happens, what's the interpretation of Bang. The introduction rule is a recipe that gives you a new copy by making copies of what's inside, what's used to make this copy. Okay, and there are different ways to interpret the Bang. It does not mean that you are making a copy; you are creating something new. So it does not invalidate the property that every object has a single reference. The second argument is that it should be possible to forget uniqueness. And so there's a more subtle argument here that if you want to do resource management, actually you need a less constrained definition of linearity. It is possible to forget uniqueness and linearity. So I'm interested in getting more into this detail, but I will move forward. And I found that key assumption was not identified, articulated, or defended, which is the idea that forgetting uniqueness has to go through a notion of subtyping. And to me, that's the key of understanding why things are like they are in this type system, not what has been explained before. And I want to propose an alternative hypothesis that actually, to forget uniqueness, you only need a homomorphism, not subtyping. So you are allowed to have a marker in the type saying that you have just shared this thing. And maybe subtyping is too strong a hypothesis, and is it worth it? And in this way, I hope we can leave the room for other necessary features of such type system, such as the notion of mutable borrows that also embody uniqueness, but in a different way. So to conclude, we've seen a lot of convergence between theory and practice. And I find that there is a coming of age of both linear logic and ownership, and we can be very excited about it. And I found that Recur works as Recur in both theory and practice at the same time. And one thing I observed with certain works on linear types is that the main result of these works is usually the proof of some internal property of a type system. But I'm going to paraphrase Gerard. A bad idea does not improve through formalization. It becomes a formal bad idea. And to paraphrase Sabine Ossenfelder, it's not because you do something that is refutable that it is science. And another point I've been trying to make is that the map is not the territory. There's a difference between linear logic and the rules of linear logic. Thank you.
Hi. So you mentioned that you don't want forgetting linearity to happen implicitly, like in a subtyping process. And
Sorry.
Yeah. Oh, I think you were saying that you don't want linearity to be able to be forgotten implicitly using something like subtyping, and you proposed that forgetting linearity should be how we do mutable borrows. So can you elaborate a little bit on this?
I made a point that is a bit different. So we want to leave space for mutable borrows. So there are lots of features. The type system is going to be very complicated. So I'm not sure I want this distinction between linearity and uniqueness. Mm-hmm. So I want to find it in a different way. So I want to be able to share something that is linear to the whole world. I want to do mutations, and then once I'm done with mutations, mm-hmm. I distribute it to the world in a copyable fashion.
So that's like freezing, right? But
freezing.
Mutable borrow assumes that you can get back the immutability afterwards.
Mutable borrows is something else. Here, the analogy would be with borrowing. Mm-hmm. So if I borrow the thing, that's something you actually can do in a Rust. I can freeze something by, so it's called leaking the contents of a box. That returns you actually a pointer to the contents. Mm-hmm. And the observation here is that if you want to make that work in a functional programming setting, you need additional rules that are those of a homomorphism. So not the full subtyping, but simply rules that say, when you freeze a pair, it's as if you froze each component of the pair, and so on.
Okay. Okay. Thanks.
Okay, while Jess is setting up, we might have room for one more question.
So I wasn't entirely clear on exactly what your opinions were about all of these case studies. Can you, is that not on? Yeah. Sorry. I wasn't completely clear on your opinions about coming out of all of these case studies. You're maybe not as provocative as I was hoping you would be. Concretely, in particular, do you think that the design presented yesterday for OCaml is the wrong way to go? Is there some alternative design you have in mind, or?
Yes, so I'm going to repeat something I said at the beginning. This talk was not about yesterday's talk. Okay. So I have more elaborate thoughts about what has been proposed for OCaml. So I made some point about the distinction between linearity and uniqueness, and I hope that there is some design space that can be explored.
And will that apply to OCaml, do you think?
Will what apply to OCaml?
This design, the results of this investigation, are you expecting them to apply directly to
I'm
OCaml?
hoping that it can apply to OCaml.
Yep. Okay. Thank you.
Okay, then thank you. And Jesse will give the next talk.
Hi, I'm Jesse. I'm from the University of Edinburgh, and I'm going to talk today about automatic differentiation via effects and handlers in OCaml. So here's an overview. First, I'm going to talk a little bit about automatic differentiation and effects and handlers. Then I'm going to introduce the main effect that I'm going to use to implement automatic differentiation and the two handlers used, specifically evaluation into normal floating point numbers and reverse mode for actually doing some automatic differentiation. Then I'm going to talk about some micro and macro benchmarks, and finally conclude. So automatic differentiation, what and why? So derivative-based optimization is important nowadays for machine learning, AI, scientific modeling, what have you. So a lot of that is achieved through automatic differentiation, which is a large family of algorithms to compute derivatives automatically based on a fixed implementation that you program. And the good thing about automatic differentiation is it's only a constant multiple slower than the original program. So if the original is 10 seconds, then the original plus calculated derivative will be like 30 seconds. There's also a wide variety of implementations and methods of implementation. But importantly, the available methods of implementation depend really heavily on the language's features. So the main idea of this work is that effects and handlers provide a practical basis for implementing automatic differentiation across the whole family. So let's talk about automatic differentiation and how we can do the chain rule in two different ways. So say we want to calculate this little expression over here, g of f of x at x equals a. So we can write that as a little straight line program. So x equals a, y equals f of x, and then g of y. And so let's look at the chain rule. So here's the chain rule from calculus. Hopefully you've seen it before. So we can calculate the derivative of g of f of x compositionally by using the derivative of g and the derivative of f. And we can make a more general version for not just two functions, but for 3 functions and n functions. And we can still do it compositionally, but now we have a multiplication of more than 2 things. And so now we can make a choice. We can either accumulate our derivatives from the right and do a right association of the multiplication, or from the left. And this is the difference between forward mode and reverse mode. So let's look at perhaps the more direct method first. So this is going to be forward mode. So we're going to calculate from right to left. And we're going to start the accumulation with 1. So what do? Well, we're going to add an additional variable to each of our original values. So x is going to get something with it, dx, and that's going to start at 1, which corresponds to the 1 on the left-hand side. Then we can calculate a derivative for y, so an intermediate derivative. So that's going to accumulate the derivative of f. So we multiply f prime of x times d of x. And next we can calculate g of y, and take our intermediate value d of y and multiply it by g prime of y. So we've calculated the multiplication for the derivative from right to left. But we can also go from left to right. But left to right is a little bit weird, because in order to calculate g prime of f of x, we need to calculate f of x first. So we can get this nesting behavior and sort of a reversal of order of evaluation for some parts. So again, we're going to have an additional variable for each of our things. We're going to have bz, bx, and by. And so bz is going to be the left-hand thing, 1, and we're going to create other intermediate variables to accumulate the derivative. So in order to calculate the derivative of g, we need to calculate f of x. And then we're going to pair everything together. So we want to also return the final value, z, g of y. And now at this point here, because we already calculated f of x, we can calculate the derivative g prime of y, and then we can also calculate the derivative f prime of x and multiply by our previously accumulated value. So the important thing to see here is that we calculate f, we calculate g, and then we calculate g prime and then f prime. So we have a reversal of the data dependency order from the original data dependency in our program up at the top here, and that's why it's called reverse mode. But how can we improve this? Well, one thing we can do to make it more efficient in practice is to make it stateful. So how can we make it stateful? We do the following transformation. So as before, for each of our original variables, we associate something which is going to accumulate the derivative. And for by and bx, we're going to start them off at 0. And for bz, like before, we're going to start that off at 1. And we do the same math as before, except now we're going to overwrite the values. Now, I say overwrite, but what we're really doing is we're accumulating into them. And so in this case, it's the same as overwriting because we're only accessing them once. But in practice, if you have a function which has more than one argument, you're actually going to do some more accumulation, so it'll have more things done to it. So this is the more general version, which works for functions that have more than one argument as well. Okay, so this is all well and good, but how do we move beyond straight line programs? Because I only talked about a very simple straight line program. And the answer is effects and handlers. So effects and handlers, just a quick overview. What and why? Well, they're really good for structured user-defined side effects. They're like catchable exceptions, but allow continuing from the thrown location. And we've seen some stuff this week at ICFP talking about effects and handlers. They also provide really good abstraction, composition, and effect reuse via the algebraic effects and handlers of them. And it also allows for complicated control flow, which is the core thing we're going to use them for reverse mode. And as of OCaml 5.0, it's in mainline OCaml, so that's great. And what they allow us to do is to get a straight line view of the operations that we care about, in this case, the arithmetic operations. So what do I mean by that? So what we want to do is we sort of want to bubble up the arithmetic operations one at a time to get a straight line view of the program. So say we have a program here. We're going to have let x equals sine of 0.5 in some arbitrary program context C, and then we're going to use that variable x in some other program context D. And what we want to do is we want to bubble up this value, or this evaluation of sine of 0.5, and calculate that first. Now, this is a valid transformation if this sine here is just the normal sine function, so a pure mathematical function with no side effects. But in practice, like we saw, we're going to need to mutate some things and do some side effects. And what effects and handlers do is they let us do exactly this, even for effectful operations. So when we have an effectful version of sine, if we implement it as an algebraic effect, then we're also going to get this exact behavior, which is what we want. And not only do we get this bubbling up to get a straight line view of our program, we can also capture the rest of the program as a first-class continuation, and then just recover the original behavior by just evaluating this continuation k with the argument. And this bubbling up and capturing of the continuation is exactly what effects and handlers do. So we can use effects and handlers to get a straight line view of our program and then perform the normal reverse mode AD on it. So what's the main effect that we're going to use? So I've called it smooth. Smooth just means you can differentiate a function any number of times that you want. So that's why I've called it smooth. And we're going to first define some helper data types to represent the functions that we're going to allow to be differentiated. So I just have a small collection here, but you can extend this to have as many number of functions as you want. So we have nullary, unary, and binary functions. So a nullary function taking 0 arguments is just going to be the constants. So given a floating point number, just have a constant that represents it. For unary operations, we have negation, sine, cosine, and e to the x. For binary, we have plus, subtract, times, and divide. And we also have another helper data type arg, which is going to help us remember if we're differentiating a binary function with respect to the left or right argument. So with our helper functions, we can define a module type smooth. So this module type smooth is going to have a type inside of it, t, and that's going to be our numeric type. So for example, it could be floating point numbers. The next thing we're going to do is we're going to register our effects by extending the extensible variant effect.t. So we're going to have 3 effects for applying functions based on its arity. So nullary, unary, and binary functions. And so we see here, for example, a unary function takes 1 argument, and it's going to apply the unary function, so it's going to give 1 result back. Similar for binary and for nullary. So we're also going to ask that we have some helper functions to actually call these effects. So C is for constant, This is for negation, so on and so forth. And then we also have some helper things which just perform these effects directly. And finally, we're also going to carry around the derivatives of the unary and binary functions. And note here, for the derivative of the binary function, we have to also specify if we're differentiating with respect to the left or right argument. So what are we going to do with this module signature? Well, the first thing that we're going to do is we're going to define a base module smooth. So this base module smooth, well, functor actually, is parameterized by a type t, which we can pass in. And basically, we're just going to implement everything that I said above. So here we extend the variant again. And now we say, for example, for negation, what is negation going to be implemented as? Well, it's actually just going to perform the effect of applying a unary function, specifically the unary function negate. And same for these other helper functions down here. So now we get to the interesting bit, the derivatives. So here we can record the derivative of all of our unary functions, so we can match on it. And if we look at the first example here, negation, the derivative of minus x is just -1. But note here that we're using the same effectful operations which we just defined. And what this is going to allow us to do is it's going to allow us to nest and inject effects into our implementation, which is going to allow us to later nest our reverse mode to create new automatic differentiation algorithms based on old ones. So that's the derivative of the unary functions, and we also have derivatives of the binary functions. So for example, for multiplication down here, the derivative of x times y with respect to x is just y. The derivative of x times y with respect to y is just x, so on and so forth. Okay, so we have our base module. Let's actually use the effects. So the first thing we're going to do is evaluate our operations just in terms of floating point numbers. So we're going to define a module evaluate. And the first thing we're going to do is just include the base module. So this just saves us some time for now. And we're going to instantiate the type of that numeric type to just floating point numbers. And now we're going to define a handler. So here's the current handler syntax in OCaml 5. So we're going to define an effect handler evaluate, which takes a computation returning something of type A and produces something of type A after handling all the effects. This clause here, return C, says what are we going to post-process our final result with? Well, we're not going to do anything. We're just going to leave it alone. What are we going to do if we encounter any exceptions as we execute? We're just going to re-raise them. And now we reach the actual effect handler part. So this effect handler here, we're going to match on all the effects that we see, but we're not going to handle all of them. We're only going to handle the 3 which we defined ourselves. So let's look what happens for handling the constant case. So for the constant case, we say, OK, if we see the effect app0 for some function n, what are we going to do? Well, we're going to be given the continuation, which we can use to resume our program. And if we see constant, which is the only option that we have now, what we're going to do is we're going to use the continua function along with the continuation k and pass that value x just back into the program. So for this case, it's very simple. And for the other cases, it's also relatively simple. U is going to be a unary function, and x is going to be a float because we instantiated the type of the type in our module smooth to be a float. And so now we can just continue the program, and every time we see an operation, we just replace it with its actual definition in terms of floating point values. Okay, so this handler isn't very interesting, but this is our base case. So if we want to take an effectful arithmetic program, we can just instantiate everything to floats and just interpret it that way. And here's how we use it. How do we use it? Well, we open our module evaluate, define some helper function that we want to differentiate, just squaring something, and then we use match with to actually handle an effectful computation. Specifically, the effectful computation is this function here. And what we're going to do is we're going to take a Boolean twice, and that's either going to apply square to itself twice or once, and then we're just going to pass in the value x, which we're going to either do square square x or square x. So here, we pass in the value true, so we're actually going to perform x to the 4th and x to the 4th at 5, and we're going to evaluate all of our effectful operations with the effect handler evaluate, which we just defined. And so indeed, this produces the correct result. So let's make a more interesting handler for reverse mode. So recall, this is the final program that we got, and I'll emphasize again the reverse dependency order. So here we have f and then g prime, and then f. And in order to create this reverse dependency order, we're going to do some interesting control flow by executing some stuff after we call continue. So for the reverse mode handler, the first thing that we're going to do is we're actually going to define a new data type of pairing a value along with its mutable companion. So here we have m paired applied to some type t. So this type t can be some other thing which supports automatic differentiation, or it can just be, for example, floating point numbers. Then we're going to define a functor, reverse. Now note this functor is going to take a module of smooth type. So reverse, the definition of the effectful operations which we're going to use in reverse are parameterized by some other module smooth. So if this module here, t, is the evaluate module we just defined, then all the operations that we're going to see in the body here will be on floats. But we'll also see that we can instantiate this module with anything else as well, and that'll allow us to nest our AD modes. So we're going to include our base module again, but this time our base type is going to be m paired of the input type. And now we can start defining our handler again. And we don't do any post-processing, we re-raise the exceptions, and now we're going to match on our effects. So again, we have three choices. The constant case isn't very interesting, so let's look at the unary case. So the unary case, what are we going to do? Well, we have our function u applied to x. So the first thing that we're going to do is we're actually going to apply u to the value part of x. So that's the thing that we get in the normal forward pass of our program. And we're also going to initialize bv to 0 like we did before. And note here that app1 and the c here are effectful operations. So these will also require some enclosing handler to actually give them meaning later. Then we're going to continue the rest of the program. When we continue the rest of the program, this value bv is going to be changed. It's going to be accumulated into, and by the time we finish this line continue here, it's going to be non-zero if there's a dependency on the values in the final result. So once we do that, then we can perform the accumulation line, which we saw in the short example program. So we can take the derivative of u at x, multiply it by the b part of the value r that we defined up here, and accumulate it into the derivative of the input of our function. And we can do the same thing, or an equivalent thing, for binary functions as well. So this is taking advantage of the complicated control flow that we can do with effects and handlers by sort of reversing the data dependency order of the original program. So let's see how we can actually use this handler. So the right way to use it is in this helper function grad. So this helper function is going to actually calculate the derivative. So we take a function f, which we're going to differentiate at some value x. And what are we going to do? Well, we're going to do the same thing we've been doing, just initialize something to 0. And then we're going to use the actual handler reverse. So what we're going to put in reverse is going to be f evaluated at x. So this is going to perform a whole bunch of effects, which is going to be handled by our handler reverse. And then we're going to start the accumulation of the derivatives by initializing this value to 1. And this corresponds to the one that we had in our example program. And then when this match statement finishes, we'll have accumulated all of our derivatives. And so the only thing that remains is to just return the derivative, the final result. So here's an example using the derivative. We have our module e, and we pass our module e into the functor reverse. So this is going to take all of the arithmetic operations we saw in the body of the reverse mode handler and make them in terms of floating point numbers. So now we define our square function again, and now we can actually differentiate our function. So here we have the same function as before, and we're wrapping it in the gradient helper function, and this indeed will calculate the correct derivative. So we have square x, x to the fourth, and this will calculate derivative of x to the fourth, which is 4 times x to the third, and it computes the correct derivative. But not only can we pass evaluate into reverse, we can pass reverse into reverse to calculate second derivatives. So here, we use a gradient here and a gradient here, and we calculate the second derivative. And I haven't shown other implementations of other AD modes, but there's a whole family. And with this method of implementing via modules, you can mix and match all the modes that you want, and everything works hunky-dory. So I'm not the first person to do this. Casey is there. Casey implemented reverse mode AD with handlers, and Casey said, I think, that he was inspired by demystifying differentiable programming with shift reset, and they used delimited continuations. But we are the first to design a larger system, and also, which I'll show soon, do tensored valued operations, as well as do micro and macro benchmarks of everything. So let's look at some benchmarks. But first, what should we expect? So there's a great book on automatic differentiation by Grievonk and Volter, and they show that for a composite measure of work, reverse mode is only a constant multiple slower than the original program. And indeed, their definition of work is quite nice. It involves memory fetches and stores, additions, subtractions, multiplications, and nonlinear operations like sine, cosine, exponentiation. And with reasonable assumptions, they prove that reverse mode should be somewhere between 3 and 4 times slower, depending on exactly what operations you're doing. So we ideally want to be only 4 times slower than the original program. So here's the micro benchmark. We're just going to calculate 1 over x. 1 over x has an infinite sum that you can use to calculate 1 over x. And we're just choosing this because we can calculate a prefix of the sum, and that can be our notion of work that we do. So we can just create a little recurrence here. So the first term is 1, and then we just multiply the previous term by minus x minus 1. So we can make just a little program to approximate the reciprocal, where we pass in the number of iterations, and this number of iterations is just how many terms of the sum we're actually doing, and that gets put into a for loop. So what we should expect is as we increase the number of iterations that we do, we should perform a constant multiple of work each iteration. So this should be on with respect to iters. So let's look at a graph and see if that happens. So indeed it does. So here we have evaluation mode. So if we just evaluate it in terms of floating point numbers, it is on with respect to the input. OK, good. And reverse mode we see is also on. So if we put these graphs together, so note here these are log scales. So the fact that reverse is shifted upwards means exactly that it's a constant multiple slower than the original program. And if you calculate it, it's approximately an 8 times slowdown. So we didn't reach the theoretical minimum of 4, but overall, it's not that bad. So we validated the asymptotics of the automatic differentiation algorithms with some micro benchmarks. Let's look at some macro benchmarks. So the best automatic differentiation benchmark suite that I could find is by Schreier et al. It's reproducible by using Docker containers. It's extensible. There's a nice test harness. And it's also realistic. So they choose 4 different tests based on real machine learning and computer vision functions. Now, the problem of what I've shown so far is that if you have one effect call for each addition and multiplication and subtraction you do, it's not going to be efficient. So the solution is to move from scalar operations to tensor/matrix/n-dimensional array operations. So I use the OWL scientific computing library of Wang et al. I extended the smooth effect and smooth module to support 35 operations involving tensors and scalars and stuff. And I extended reverse mode to handle these new operation types. So specifically, we implement one of the objective functions in the benchmark suite for Gaussian mixture models. And the input to the benchmarks has 3 parameters, n, k, and d, where n is either 1,000 or 10,000. And k and d is actually the total number of input variables which we're differentiating against. So the x-axis in our graphs is just k times d. So here's all the tools in the system. There's a lot of different languages and a lot of different approaches. So there's manual approaches, which is just calculate the derivative on paper and write a program which calculates the derivative. So theoretically, these should be the fastest, one would hope. There's also finite differences, which is just f of x minus f of x plus a little bit divided by that little bit. And that's a really bad way of doing derivatives. So this is here to show you that hopefully all the AD systems do better than that. And then there's a whole bunch of other stuff, including industry standards like TensorFlow and PyTorch. So what do I mean by static and dynamic? In automatic differentiation, you can sort of do 2 big classes. Static basically means that you evaluate away all the control flow to create a static computation graph, a DAG, and then perform differentiation based on that. And you'd expect those to be relatively fast because you don't need to deal with any dynamic control flow. And dynamic means you're still retaining dynamic control flow, and as you go, you create some structure and then do something based on that. And so you'd expect usually, although in the graphs we'll see it's not always the case, that dynamic is going to be slower than static. And the work that we've done here is definitely dynamic. So ignore those red triangles for now at the top. Here's the OCaml stuff with handlers. And n is 1k at the moment, and the variables k times d are at the bottom. And also note this is a log-log graph as well. So let's compare it to the manual implementations. So we see here, okay, all the manual implementations in C++ are quite fast. And the finite differences is the one that's really bad up top. And that just shows that if you want to calculate a derivative, don't use finite differences. It's really bad. Okay, so let's look at the static implementations. So we can see here that pretty much all of the static implementations are doing better than us as well, except for some reason the Julia Zygote library is having a bit of a tough time, but I'm positive for Julia that the newer libraries are going to do better. But the benchmark suite is a little bit old, so Enzyme and some of the other newer stuff isn't in the benchmark suite. So let's go to the ones which we really should compare ourselves against, the dynamic ones. So for the dynamic ones, we're doing a lot better. So we can see here we're pretty much the same as eager TensorFlow, which is dynamic, and also the diff-sharp library in F-sharp. And here's another Julia stuff going on over here. And then we have PyTorch. So PyTorch, turns out, is really, really, really good. I talked to one of the authors, Adam Paschke, this week, and I'm like, oh, why is PyTorch so fast? Because in fact, PyTorch is even beating the manual implementations we can see when it gets higher. And his answer was, we spent a really, 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 really long time and a lot of effort making it really fast. And yes, so PyTorch wins. And indeed, when we look at the other set where n is 10K, PyTorch still wins. And here we see TensorFlow starts to beat us a bit, but then it either runs out of time and memory, so I don't know exactly what's happening there, but yeah. So conclusion, there's actually a lot more to say on AD and effects handlers. You can look at my thesis, so there's many different modes. So there's checkpointed reverse mode, which does a time and space trade-off. There's also higher order functions and higher order derivatives. There's also different languages, some with effect type systems, which can help you avoid some AD-specific bugs. So in my thesis, I also look at Coca, Frank, and F. And there's also mathematical correctness to consider. So using denotational semantics, I prove forward mode and a simpler, non-stateful reverse mode correct. So AD and reverse mode AD in this talk specifically requires complex control flow. Effect handlers enable a simple implementation which follows the math. And with a little effort and moving to tensor-valued operations, we are competitive among similar tools. So future work, I didn't realize this, but PyTorch, its C++ backend, which is the fast bit, actually has bindings in OCaml. So I tried this week to switch my bindings from OWL to the Torch bindings, but I didn't have enough time. So that might actually get us a lot closer to the PyTorch stuff, so we'll see. Also, I want to prove correctness of the stateful reverse mode, which requires doing some more work behind the scenes, and also custom functions. So if you implement a function, you can have AD calculate the derivative for you, but for mathematical reasons, you might know a method of calculating the derivative which is a lot faster. So putting custom function derivatives can be quite useful, and that might actually involve higher order effects. And you can read more about some of the stuff I talked about in the preprint. Thanks.
Yeah, I have at least one question. So your effect handlers do not have the continuation call in the tail position.
Nope.
Does that mean that the stack usage is proportional to the sequential length of dependencies in the program?
Yes, so actually Stephen Dolan helped me out. So if we look at the example usage somewhere, you need to increase the garbage collector minor heap because indeed the amount of continuations you use directly increases the stack size. And so if you're not careful, you repeatedly go over the minor heap and create quadratic behavior. But I've been told that this is a sort of long-standing, I removed the slide actually, a long-standing thing in OCaml where that was sort of always the case, and now with the addition of effect handlers, sort of needs to be changed a bit so that this quadratic behavior doesn't happen. But in general, reverse mode AD is supposed to be linear in terms of memory usage, and so it's still correct with respect to the asymptotics, and with a change to the GC, you can still get the correct behavior. Yeah.
Maybe Stephen sitting on? Just a question. So what happens if your function you want to differentiate is parallel, uses multicore, for instance? Then
this doesn't handle it at all. And I think so for automatic differentiation, there's definitely a lot of opportunity for parallelism, both in the basic operations, if they work on arrays, and also in general, because ideally you're differentiating pure mathematical functions, but this work doesn't talk about anything related to that.
So yeah, you say you got the asymptotics right. Have you done more detailed performance analysis to see where these overheads are really coming from? Like, is it from the GC? Is it from the effects
No.
implementation?
But that's some good future work to look at. Yeah, thanks.
Thank you.
Okay, let's thank And now we'll hear about rethinking the value restriction.
If I can get my mouse cursor back onto the screen. There we go. Okay, thank you. So I'm going to be talking about the Hindley-Milner type system and the value restriction, the type system at the core of ML. So I understand that some of you may have heard of this type system before, but bear with me, I promise I will say something new about it. Not right now, though. Right now, I'm going to say some very, very old things about it. So the key idea in ML is, of course, that you don't abstract over polymorphic values. There are no for-alls on the left of function arrows. So that means you can define polymorphic functions, you can use polymorphic functions, but you can't abstract over polymorphic functions. You can't pass polymorphic things to other pieces of code. So this splits the world into monotypes, which I'm writing with tau, which are the types that don't have a for-all in them, and type schemes, which I'm writing with sigma, which are the types that may have a for-all in them. And then the rule for typing lambdas makes sure to use a monotype for the argument. And this is the key simplification that makes type inference work so well in the Hindley-Milner type system. So if you look at the original typing rules, like the Damas and Milner 82 rules for this, you'll see that there are two rules for polymorphism. There's generalization, where you can quantify over a for-all that's not used in the context, and instantiation, where you can get rid of a for-all, filling in a type of your choice. So these rules by themselves don't define an algorithm. You can't write ML purely off that. To get from here to algorithm W, there are two problems that you have to solve. The first one is, during the instantiation rule, what should I choose? Which type tau would be a good tau to replace with the alpha? And the answer to that is, of course, the theory of unification and most general unifiers, and flexible variables, and so on, none of which I'm going to talk about today. The other problem that you have to solve when implementing this type system is, where should I do these two things? When exactly should I be instantiating stuff, and when should I be generalizing stuff? And to help us answer this question, there are two simplifying principles. And these are really, you can kind of squint and see them in the implementation of algorithm W in the original work, but they were, I think, explained in more detail by a later paper by Tofte. So the two simplifying principles that make ML really implementable are, first, pre-next polymorphism. Rather than allowing for-alls deeply nested inside things, we say that the for-all symbol occurs only at the very top of a type. And we can get away with doing this because this doesn't actually lose anything. We don't actually lose any expressivity. There's nothing is lost here because type with a more deeply nested for-all. Again, I'm only talking about deeply nested on the right-hand side of an arrow. We're still obeying the ML rule of not having any for-alls on the left. But a type like the one on the left with a for-all more deeply nested is completely equivalent to one that has the for-all at the top level. So that restricts the shape of types, so you don't have to think so hard about where to place the for-alls. The second important simplifying principle is let polymorphism. So that's the idea that we don't lose anything by delaying all of our generalization to let and doing all of our instantiation at var. So the intuition here is let is the latest possible point that you could generalize, because let is the point where you're about to give a name to something, and that's the point where you might potentially use it twice. Up to there, just before let, there's not really any benefit in generalizing it, because generalizing it allows you to use it in two different ways, and if you're only going to use it once, then that doesn't matter. So you end up with these versions of the rules, which again, if you kind of squint, you can see them in algorithm W. They were published in this form a bit later. And these are a little bit more complicated because they glue together two rules from the original type system. The one on the left is letGen. It's the one that does generalization right before putting a variable in the context and giving it a type. And the one on the right is varInst. It's the one that pulls a polymorphic type out of the context, instantiates all the variables, and then gives you a fully instantiated type. And the reason these are used is, firstly, this now defines an algorithm. It is completely unambiguous where to do your generalization and where to do your instantiation. And secondly, again, nothing is lost. We didn't lose any generality. We didn't lose the ability to type check any particular programs. This is completely equivalent to the original system, but much easier to implement. But of course, a problem arises on the first extension that you do to ML, which is the attempt to add mutable references. And if you add mutable references and you use the standard gen and inst rule, or even these versions for letGen and varInst, then if it is done completely naively, the resulting system is unsound. So usually this is blamed on something to do with side effects or mutability. But a point I'd like to make here is it's not actually about side effects, it's about sharing. So to demonstrate this, I'm going to give an example of the problem showing up using a feature that has nothing to do with side effects. I'm using local exception definitions from OCaml. So if you type this into OCaml, it will correctly reject your program because this is a bad program. What I'm showing here is a demonstration of a broken compiler because, of course, I develop OCaml. I am a professional producer of broken OCaml compilers. So here is a particular broken one in which I've implemented the naive ML generalization rules. And here we've got a function which locally defines an exception E, which takes a parameter of type A, and then produces two functions. One of them raises the exception E, and the other one catches the exception E. But if we're allowed to generalize the type A using the normal generalization rule, then I can, on the first half, with the first F42, I can raise the exception, passing it an int, catch the exception, assuming it's a string, and then print an int as a string and explode in a predictable way. So what's going on here is this generalization rule. This generalization rule is saying it's safe to generalize if the type variable alpha does not appear in gamma. And what it's really trying to say is it's safe to generalize if all of the uses of this value won't share the alpha. They all get to talk about different alphas. And the assumption in this rule is that all sharing shows up somewhere in gamma. But when you have features like fresh exception types or mutable references, then you have this form of sharing, like the different uses of the same value can share something important that depends on the type, and it doesn't appear anywhere in gamma. So this was annoying, and there was a cottage industry of different approaches to working out how to ban things like this while not restricting the type system too much. And the one that everyone settled on after a while is one of the simplest. It's Wright's value restriction, which says that generalization should only happen on syntactic values. So I slightly prefer the words used in the standard ML definition and also used internally in OCaml for this, which is non-expansive terms, so that they're, rather than just being values, they're things which, when you evaluate them, the store does not get any bigger. You don't allocate any references or make any new types of exceptions. You don't make anything that can refer in a shared way to the type that you're trying to generalize. So that means that the letGen rule gets even more complicated. We now have, as well as the stuff that we saw in letGen, we now have this additional val thing, which is that we can only generalize if v is a syntactic value. And this is just mildly annoying. It's not like the biggest thing in the world. The system is fine. I use it every day. But just constantly, I have to explain to an OCaml programmer why their program didn't work. And as, like, even to people who understand what they think of as the type system, but no, there's this extra thing off the side, this definition of a syntactic value. So I'm going to talk about a different approach to this, about rethinking how the values restriction should work, that will end up with a simpler definition. And it will type a few extra programs, but that's not really why I'm interested in this. I'm interested in not having to explain the value restriction ever again. So the really central point is to go back to those two simplifying principles, prenex polymorphism and let polymorphism. So prenex polymorphism, the idea that all of the for-alls may as well be at the top of the type and we don't lose anything, and let polymorphism, the idea that all of the instantiation may as well happen at vars, and all of the generalization may as well happen at lets, and we don't lose anything there either. The proofs that those were okay things to do, those were all about the pure ML calculus. Those were before we added references. But what if we have references there from the beginning? What if we have mutable state and exception things and so on? It turns out both of those principles are just false. For instance, with pre-next polymorphism, if we have references, those two are just different types. The type on the left is a perfectly well-behaved function. That's a function which, when you call it, it gives you back a reference containing, say, an empty list that can hold alphas. And every time you call it, it gives you back a different reference. So every time you call it, it can give you back a list capable of holding a different type. So it really is for all alpha. The thing on the right says that you call it once, and it gives you back a polymorphic reference that can hold any sort of list. And that's completely unsound if such a thing were to exist, because I could get back this one reference, put in a list of ints, pull it out, and expect it to be a list of strings. So the idea that we can hoist all of the for-alls up to top level is simply false when we have mutable references. We really do want to distinguish these two types. The second one, the let polymorphism, it is also false that we can just do instantiation of variables and just do generalizations at lets once we have mutable references. Here is an example of like a perfectly well-behaved program, which OCaml currently refuses to type check. It says, it defines a reference. It defines a function which takes an x of an unknown type. It also allocates a reference. The reference is an int reference. Its type does not depend on the type variable being generalized at all. So if we were able to use the really old school separate gen rule, we could generalize the function as soon as we see the lambda, and it says, well, it takes an alpha and returns a pair MLs actually implement. This thing does not type check, or at least type checks with only a weakly polymorphic type, because that ref shows up before you're allowed to use generalization. So this idea that gen can safely be delayed is just simply untrue. So what I'd like to talk about is a different approach to type checking ML or ML-like languages, where we move away from this idea that instantiation must be done as early as possible and generalization must be done as late as possible, because I don't think that's the right approach for a language that has side effects and references and exceptions and so on. So we're going to move to full rank 1 types. So what that means is we're going to allow for-alls, again, still ML, still no for-alls on the left of arrows, but for-alls can appear on the right of arrows or inside tuples or in covariance positions generally. So these are the original rules for ML for the subsumption relationship. So this is this type more polymorphic than that type? So for monotypes, well, T is the same as T, but the two things that we're allowed to do are we can instantiate for-alls on the left. So if there's a for-all is more general than any of its instances, and we can take apart for-alls on the right as long as the variable is fresh. So that's a rigid Skolem variable being used on the right-hand side. To get from there to rank 1, we have to add 2 more rules that say we're just allowed to walk down the right-hand side of functions and into tuples. So that means that for-alls are, like, we can do instantiation and rigid Skolem comparisons inside the right-hand side of functions or in the other side of tuples. So this is not particularly new. This is actually, this part of what I'm describing is actually implemented in the SML sharp implementation of ML. So as an example of what that actually means, let's look at these 2 types. So they both describe a curried function of 2 arguments, taking an alpha and a beta and returning a beta, but they differ in the placement of the for-alls. Now, the old school way of doing this, of interpreting these 2 types, is all of the for-alls are implicitly hoisted. And this is, for instance, what Haskell used to do before GHC9, a feature that was removed known as deep subsumption. You could say that these are unrelated types, that these don't unify, these are different. And this is actually what Haskell does at the moment for, I think, technical reasons to do with the quick look in predicativity system that they now have. But the approach I'd like to describe here, the one that's true rank 1 subsumption, is when they're related but not equal. Q is in fact a more general type. And the reason for this is Q actually offers more power to its users. Both of them allow the user to choose alpha and beta, but the type Q allows beta to be chosen later. a user of P must commit to a particular beta before applying the first argument, but a user of Q can choose beta after the function has returned. And this is the key idea. This is really relevant to whether this is sound in the presence of references and so on, because what if Q allocates a new reference before it returns its value? So this makes our problem of deciding when to do things, the original problem of where to put generalization and instantiation, a little bit more complicated. So we have now this general subsumption rule. We can, at any time, make a type a little bit less polymorphic by filling in some of its for alls. And the rule that we used to have, the var inst rule of doing all of it as soon as we can, is no longer the most general thing to do. And what we end up needing to do is, instead of doing it eagerly, we do it lazily. We instantiate the for alls only when we really need to. So only when we're trying to call a function and there's a for all in the way of the arrow, or we're trying to access a field of a tuple and there's a for all in the way, only then do we actually instantiate the for all. So it does mean that we actually get slightly more straightforward typings of very simple rebinding definitions like let f equals g there. So in a normal implementation of ML, let f equals g is type checked with let inst or var inst and let gen. It fully instantiates the type of g, then gets to the let definition of f, then regeneralizes it all. But if we're doing this lazily, then when we see g, we just leave it with a for all in there, and when we see the let, we just put the for all back into the context. This is actually, so again, doing this style of instantiation as lazily as possible is also not a particularly new idea. It showed up in a fairly well-read paper by Neil Krishnaswamy and Janet Dunfield of Complete and Easy Polymorphism, where I'm told by the authors they didn't realize they were doing something new because they had assumed this was the standard way of doing instantiation. Just this, do it as needed, rather than doing it all in a big bang as soon as you see a variable. But the bit that's more interesting, the bit that is really the key idea of this talk, is the other end. What happens about generalization? So the standard ML with the value restriction is to instantiate as eagerly as possible and delay generalization as late as possible until let. And we've seen now that we want to instantiate alpha like we want to instantiate alpha lazily rather than eagerly, and correspondingly we end up having to make changes to generalization as well. So the original generalization rule with the value restriction looks like this. It says we can generalize something with the normal rules for the variables must not appear in the context, only when it is a syntactic value. So a syntactic value is something like a lambda expression or a tuple construction where all of the components are themselves values. So let's just split that into cases. Let's consider the different sorts of things that we might be generalizing independently. So for lambda abstractions, well, a lambda abstraction is a value regardless of what's in the lambda. So there's no particular complicated side condition there. We can just generalize lambdas. For gen pair, then that requires its subterms to be values. But since we're no longer delaying generalization until the very end, since we're allowed to do generalization wherever we want, and the parts of v1 and v2 in that tuple are in fact already values, then they will already have been generalized before we get to this rule. There will already be for alls in the types of the components of that tuple. So this rule isn't actually getting us anything. This rule allows us to put a for all outside the tuple, but because we've got rank 1 subsumption, that's actually less general than putting it inside. So our type system loses nothing by just completely deleting that rule, and in fact, every other rule for generalizing values other than lambda. So what we actually end up with is generalization is a thing that happens to functions. So the type system is you instantiate for alls when you're absolutely forced to, when you're trying to use something that's got a for all in the way, and you generalize when you see a lambda. So for I'll give a couple examples of what this ends up looking like. So here, a very standard ML function. We get the same type as we would in ML. We get it for a slightly different reason. The generalization happens because I see a fun, rather than it being ungeneralized until I see the let, but it gets the same answer. Here, we don't generalize, so that's ref of tau rather than for all alpha. That's a variable that we have not generalized yet. And at this point, I would now normally have to do a big digression about the nature of syntactic values. But in this system, I say, no, it doesn't generalize. There's no fun. There's no lambda there. Lambdas are the thing that make polymorphism. Here's the example from earlier that OCaml fails to type check, or fails to give a sufficiently polymorphic type to. And this one is type checked with the most general type because the for all appears where the fun is. The lambda is the thing that makes for alls. Here's a more complicated thing, which makes an identity function, packages it up with a reference, then pulls it out again. This thing also gets the most general type, because again, the for all appears where the fun is. Lambda is what makes for alls. So this is a pair of a for all alpha, alpha to alpha, and a reference. And we throw away the reference, and we are left with a for all alpha, alpha to alpha. So, I mean, these are not especially compelling examples. I'm not saying that this is a better way of doing it because we get to type check these two functions. They're not things that people normally write. But I just really like to have a type system like this so that I would never, ever have to explain what the value restriction is. So in general, if we switched to full rank 1 types for ML-style languages and dropped the assumptions of pre-nex polymorphism and the assumption of let polymorphism, then the type system says we generalize all lambdas rather than some lets. We don't need a syntactic value judgments, and yes, we can type a few more programs, but not especially interesting ones. Thank you.
Yeah, thanks for the nice talk. Can you go back to the previous slide? Yeah. So here you're saying that you allow nesting the for inside the pair component type.
Yep.
Right. So do you have some? Do you have a subsumption for pairs? Like you have subtyping rules for pairs and stuff like that? Yeah. Right. Okay, but so this works because the pair is covariant, right? So
yes.
what happens if you don't know that? Like, so you need covariance annotations on your data types now, right?
Yes, I mean,
if it's
yeah, because the point of rank 1 is that for alls can appear under covariant positions. It's still ML, so no for alls left of an arrow. So yeah, you really do need to know that it's covariant for this to
right,
work.
but in OCaml, sometimes you don't know if an abstract type is covariant or not, for example, right?
Oh yeah, that's true, and you would not get for alls under
in this case. So in this case, what happens? You'll have to instantiate the for all, and then you have to explain that to students, right, or to programmers. So you don't explain the value restriction, but you have to explain covariance and the fact that sometimes the lambdas get instantiated for some reason, right?
Yeah, I'm mostly happier explaining variance than explaining the value restriction. Your mileage may vary.
That's good. I agree. Yeah, so it's good to see that you came to the same conclusion. We're already doing this in ML script, right?
Oh, cool.
And I think there were previous systems that generalize lambdas and instantiate at applications, because that's the only way that really makes sense, at least in the call by value semantics, right? You don't need to generalize other things than functions, really.
Yep.
Yeah, okay, thanks.
Hey. So I had a couple of small questions. One was, so with the arrows, obviously you can instantiate in and not out, like that's assumption, unless you push the for alls in. With the tuples, presumably you could move them in and out a little, you can go both ways. It's kind of fine because there's no way to do anything between. Sorry. Presumably with the pairs, putting the for all just inside the pair and the for all just outside the pair.
That's true. I mean, it's not the system I'm describing here, but I agree it would be sound to allow for alls to float in and out of tuples.
Okay. Is there anything that makes it trickier? You just not thought about that, or doesn't really matter?
Yeah.
All right. And the other one was so another thing where you end up needing polymorphism is obviously row polymorphism kind of generates another kind of constructor that there's you write if I write something that's just a bunch of polymorphic variant constructors and no lambdas at all, I still need that to come out polymorphic to get the row polymorphism. So what's the rule?
Oh, right. So would you mind if I switch to a simpler example of empty list? Because I think
sure.
it's the same kind of problem, or are rows super interesting here?
Probably the same. Yeah. Okay.
So yes. So some of these. So there's some types which in ML, for instance, if you have an empty list constructor, the type checker will give that a flexible unification variable and hope for it to be generalized later. But in this style, we're doing generalization as eagerly as possible, so we can't rely on generalization happening sometime later. So it means the typing rules for things which are completely polymorphic have to actually say the for all up front. So the rule for nil is nil has type for all alpha list.
Gotcha. Yeah, that makes sense. Thanks.
Very nice system. I think it's much simpler, much more elegant. But that raises a question in my mind of why haven't we been doing this all along? In terms of like, I would kind of expect historically that something like this would have been developed first rather than let generalization. So what is the fundamental trick that you had to do in order to make this possible that we didn't realize before?
Yeah, so partially I was hoping that someone would say, we've been doing this for 20 years and you haven't found the paper about it, because it's weirding me out that we haven't. I think maybe the thing that's a little bit, I suppose, unusual is there's a non-trivial subsumption relation, so you have to think a little bit about deeply subtyping things. I don't think it's that hard to do, but maybe that might have put people off who came across this before. But yeah, I don't really have an answer to that one. I am wondering about it as well.
On the topic of non-trivial subsumption relations, have you thought about extending it to subtyping? And so instantiation is then just in the subtyping relation, which is not normally the way that, say, languages like Java or C# handle things. They would separate subtyping from instantiation, but does this give you a way to do that, sort of integrate it?
Yes, yeah. I mean, much as Lionel said earlier, I think both of us noticed this sort of thing from doing exactly that in a language of subtyping, and this is me backporting it to ML by deleting all of the stuff about subtyping.
Okay. Hi, thank you for the story. I like the story. Just two independent remarks. In MLF, actually, we do the same thing. We always generalize as soon as possible and only instantiate by need. So the P and Q, we would give a more principal type Q rather than P.
Oh, yes.
The other independent comment is that actually, your example, we can already type in ML. So this is not implemented in CAML, but one of the first prototype I wrote in ML is actually doing not only non-expansive values, but it's doing in the negative way. So you're allowed to generalize everything except what is forbidden to generalize, and then you recover all these examples.
Right, so this is the rule where you can walk down a let binding as long as the thing being bound doesn't mention the...
Yes, so what is forbidden is type variables that would appear in an expansive expressions. So everything can be generalized except they appear somewhere unprotected in an expansive expressions, and I think you recover the same example.
Yes, so that's this example here where the ref is, because the alpha, it doesn't appear anywhere to do with refs. Exactly. Yeah, that works as well. Yeah, thanks.
Thank you for the presentation. First, a small remark here. So you mentioned that it was in SML#, if I remember correctly. Oops. Or recall that rank 1 polymorphism by opposition of rank 0 polymorphism that was the traditional ML style.
Sorry?
Ori, the author of SML#, called that rank 1 polymorphism. By opposition, he was calling rank 0 polymorphism what you get usually in ML.
Yes,
okay. And the question that you would expect from me, how does it interact with the relaxed value restriction?
Yeah, I have not proven this. Actually, so in many of the cases where the relaxed value restriction allows you to give polymorphic types to things which produce empty lists, or things which produce data types which mention their type variables only covariantly. In many of the examples that the relaxed value restriction type checks, you can get the polymorphism deeply at the point of creation of one of those empty structures, but I don't know whether that covers some of the motivating examples of the relaxed value restriction, but I don't know the relationship between this and the full system, whether it gets the same generality or not.
Okay.
So one of the most annoying cases for the value restriction is when you partially apply a curried function that you know is going to return a closure immediately. So I'm not seeing how this handles that.
So
particularly in the case, I understand it can sometimes handle it, but in the case where, say, the function has the type for all alpha arrow something, and then several other arguments, and you instantiate that first argument.
Oh, I see. Where it really does the first argument really does.
The first argument already has the
yeah. Okay. So in that case, it's not going to help because in that case, you really might be doing the bad thing. That function really might be creating a mutable reference.
Right.
In cases where it doesn't mention it, you can use the type that pushes the for all to the right.
Okay, so you'll still have to explain the value restriction in that case. I mean, basically, that's a case where if you knew that the function was total, then you wouldn't.
Yeah, no, that's true. There's still something to explain there. I think the reason that I like this approach is that I can explain that distinction by pointing at the types and saying the for all is there before the argument rather than there after the argument, but the limitation absolutely still exists.
So currently, when you have something like a reference to a formatting function, I think it's a little bit awkward because you have to do it like the logs module does. You have to define a record with a single field and put your for alls there. Would your system allow an easier way to write those kinds of?
No, it's still so. So the initial ML style assumption of no for alls left of ours means no for alls in positions which aren't covariant. So that includes inside references. So it's still, for things that actually go into references, it's still just as restrictive.
Okay. Okay.
Hi, could you go back to the examples because I have some question. In the last example with the first function, here you need to instantiate this first function because the first component of the bar is polymorphic. So how you avoid breaking the prenex form here? Because you substitute.
No, sorry. Excellent point. I should have been a bit clearer. I'm using a syntax for a primitive projection.
Okay.
Yeah, you have that if you actually. Yeah, if you lambda expanded, eta expanded first, then that becomes tricky because you are trying to pass a polymorphic thing to a function. Yes.
Yeah. Thank you.
Okay. Exciting. Thanks.
Thank you.
Oh, Jesus. Look, the border went onto one side when I locked and unlocked. Yeah, it's still.
It's so interesting.
It's so fucked. Whatever, I can live with it.
Yeah, no one's going to notice. Why is that not?
Oh, well, that's now turned off.
Oh, I think it's just not plugged in properly.
I think that might have come unplugged. And now the border will probably reappear, right?
Oh,
Yeah.
Got any questions you want to plant?
No.
Okay.
I'm just hoping I can.
I'll just think of something really difficult then.
Just got to remember. I don't know. I don't know. And I say that. Do not disturb is on.
You know what they say?
Don't.
Never admit when you're unsure.
Of
Overconfidence is the power to...
all the places bullshit.
Yes.
This is a tough one.
Hello, everyone. We are back for the third session of the ML Workshop 2024. It's my pleasure to introduce Ethan Range, who works with Jeremy Yallop on safe pattern generation for multi-stage programming.
Hi, everyone. My name is Ethan Range, and I'm going to be presenting some work that I did as part of my master's dissertation at the University of Cambridge, supervised by Jeremy, on generating pattern matching expressions in multi-stage programming. And so, for the benefit of anyone unfamiliar, I'll start with a little bit on what multi-stage programming actually is. So, multi-stage programming is a variety of metaprogramming. What is metaprogramming? Well, metaprogramming is ways of generating code in which we can have representations or fragments of the code as data within our language and separate that compilation out into multiple stages. in this work, we use the style of multi-stage programming found in the OCaml language. In particular, we can take some expression of a type A and take a quotation of that to get a code fragment of type A code. And we can also splice one of these code fragments back into the program. So if we have a code fragment of type A code, we can splice it back in to get the underlying A expression. And OCaml also provides the ability for us to run these code fragments with the run operation, which simply takes a code fragment and executes it. One of the things which is quite useful for multi-stage programming is optimizations and generating optimized code. And so we'll turn to look at a type of optimization called list map unrolling. And we can define the higher order map function over lists as in the classical way. So mapping a function onto an empty list gives us an empty list. And in the recursive case, we apply the function to the head of the list and cons that onto the recursive call on the tail of the list. But what we can actually do in order to get a performance improvement is we can take this map function and we can actually unroll this recursion. So instead of processing a single cons cell at a time, we can instead process multiple cons cells at a time and append them to the front. And what we also have to do is we need to add a catch-all case at the end for applying the map to any lists which have a length shorter than the depth of the unrolling. And what's interesting about this unrolling is we can actually do this to an arbitrary depth. So here we've unrolled it one level, but we can actually unroll it as many times as we'd like. The interesting part of this is that depending on precisely how we're using this map function, the data which it operates on, and potentially even the hardware of the system which we're running on, the optimal depth for this unrolling is going to vary. And so it might be quite a nice idea to use staging as a way to generate different versions of this map function on the fly to ensure that we're using the one with optimal performance. So we can have a look into some ways of doing this. Well, one approach we might look at is using an untyped multi-stage programming system. So an example of this would be the untyped template Haskell. And this is very nice. It provides us the tools we need to be able to build up these arbitrary patterns. The problem we run into is that suddenly we've thrown away all of the guarantees we have about the well-typeness and the well-scopeness of the code we generate. And this isn't ideal. So we might look into a type metaprogramming system, such as OCaml. And OCaml does indeed provide ways of generating patterns. As we can see here, it actually is quite clever and it exploits the OCaml syntax to define cases of a pattern matching expression as a code fragment, which is a function. And here we define both the pattern and the body as part of the function. And this is nice. This allows us to define a certain class of patterns. But if we want to try and apply this to our case of generating list maps, we run into an issue in that every single pattern which we use in a case must be statically known up front and defined. There is no way to kind of build these on the fly based on some dynamic value. And so what we're really looking for is a more powerful way to build up patterns and pattern matching expressions in metaprogramming. And that's precisely what we set out to do with this work. So we want to build up, we have a system which we can, in a type-safe way, build up arbitrary patterns. And we want to do this by having a much more modular approach to building up patterns and bodies. And I'll touch on exactly what I mean by that later. So in order to do this, we have 4 main steps. So first, we're going to need some way to actually define these patterns. So OCaml provides their very atomic way in which we can state up front, but we want a much more flexible modular way of doing this. Once we've actually specified our patterns, we're going to need some way to describe the bodies. So OCaml does it with a fragment of code, except we're also going to want the ability to bind variables within a pattern and include these within the body. Once we've got both a pattern and a body, we then need to look into generating cases and generating code from these cases, all at the same time ensuring that the code remains well typed and implementing the appropriate checks. And finally, once we've achieved this kind of parity with OCaml, we need to look into the idea of generating these statically unknown patterns, which we'll need for the map functions. So we'll first look into the idea of describing patterns. So as I said, OCaml does provide a safe way to define patterns, but it lacks the modularity. And here's precisely what I mean by this, in that we may have patterns such as this with an x cons and x's, and also a tuple of x1 and x2. And it's quite conceivable that we might want to build a pattern from these in which we can substitute the x1, x2 tuple for the x. Unfortunately, that's not actually possible with the way OCaml is implemented. And so what we introduce is the idea of a domain-specific language to specify these patterns in which the terms can be used to build up an arbitrary pattern. And so, as I show here, there's a subset of our DSL in which we can define many of the common patterns which are found built into OCaml. So, for example, we can define wildcard patterns, integer constant patterns. We can find variable identifier patterns. And we notice actually that instead of actually explicitly having to name the patterns as you would in OCaml, we can instead describe a pattern as a variable and don't actually need to have an explicit name and allow that to be generated instead. We have empty list patterns, more constant patterns, and then these compound patterns, which allow us to combine two existing patterns to produce a new one. So on the left is, of the two is the tuple pattern. So if we have two given patterns, we can match on a tuple of those two. And on the right is a list cons pattern to do very much the same. And it's quite important to type these patterns to ensure that we only generate valid code at the end. So there's a few reasons why we will do this specifically. Perhaps the most obvious is that some patterns are completely invalid to be even thought of. So it's very reasonable to think of consing an integer onto the tail of a list represented by a variable. But actually, it makes no sense to cons something onto an integer constant. And so we need to make sure we can reject patterns like that on the right. But then there are other issues. So we need to make sure that the patterns we define are compatible with the bodies which we pair them with, and also make sure that all the cases within a pattern matching expression are compatible in both their input and return type. And we'll revisit that idea later. So in order to do this, we introduced the idea of a pattern type. And this has 3 type parameters in it. So the first, the A, is perhaps the most simple, and it's simply the input type of a pattern. So if we have a pattern which matches on an integer constant, that can't be compared to against with a string, for example. Then for the next 2 patterns, which we'll explore in a bit more detail, the F pattern is what we call the pattern body context type, which is effectively a type which represents what types of bodies this pattern can be paired with. And finally, the R type is the return type of the body of a pattern matching expression. Now, it seems counterintuitive that why would the pattern need to reflect what the return type of the body is, but we'll come back to that later and see that it is in fact necessary to have that there. So now we've got a way of specifying patterns. We can look into the problem of specifying or defining pattern bodies. So given that the body is just a code fragment, it may seem as the most natural approach to simply define the body as a code fragment. However, what we want to retrieve from OCaml's implementation is this ability to introduce bindings in the pattern and have them present in the code fragment which represents the body. And so in order to do this, we have the idea of representing the pattern body as a function. So this function takes the form as shown, and we effectively use the parameters of the function to represent code fragments, which are the variables bound within a pattern. And then the return type is the body of the expression which represents the body. And so a couple of examples of this, if we have an integer constant 2 pattern here, we see that actually we bind no variables, and so the function has no arguments, and we can return a code fragment of just a Boolean, for example. Whereas if we have a tuple of variables pattern, we see we have the x and y, which correspond to the 2 variables being bound, and we can show that we can use these pattern variables to actually do something in our body here, adding them together. So if we look at this pair of variables again, we can see that if it's combined with the addition body, we can see that the input type is going to be constrained to be a tuple of integers. The integers because they must be added, and the tuple from the shape of the pattern. If we look at the shape of the body, we see that we have two code fragments of integers representing x and y respectively as the parameters into the function, and then we return a result type, which is the fragment of an integer. And again, you'll see that the R type is in fact just a duplicate of the return type of this f function. But again, we'll see very shortly why that's necessary. So if we look more generally at our DSL terms, we can start typing some of them. So for an integer constant pattern, if we provide it an integer on which it should match, we constrain the input type to be an integer. We can't pass a string to an integer constant pattern. But we actually impose no restrictions on what we do with it in the body or the return type of the body. If we consider a variable pattern, actually we don't constrain the input at all. Our variable identifier can match onto any type of value. But what we do is we introduce a new binding. So this variable gets bound and is available in the body. And we don't actually constrain the return type in any way. And now on to why we do actually need this R type in the pattern. Is the idea of the compound patterns. So this is the tuple pattern I mentioned earlier. And we use a approach based on difference types in which effectively we take the combined pattern, the tuple A and B, and the input type is simply a tuple of the input type of the first and the second pattern. But for the function type of the combined pattern, if we apply if we provide values for all the bindings in the first pattern to this combined pattern's body, we need to end up with precisely the function which encodes the body of the second pattern. And that's the reason for shaping that. And there's much more on that in both the paper and my dissertation. So now we actually have both patterns and pattern bodies generated. We move to the idea of generating cases and generating code from these to do something with them. So if we have both a pattern and a body, we introduce this idea of the arrow operation. And this just says to us, if we have some pattern which is expecting a body of type F, and we provide it a suitable body of that type F, then we can produce a case of this. And that's just a case in a pattern matching expression. Now, the A and the R type parameters in this case are doing exactly the same as the A and the R type parameters in the pattern type, namely the input and output type. And you'll notice that the F type has been dropped. And this corresponds to the idea that the variables are bound within the pattern. And once we're outside of the pattern body, we no longer need them and they're dropped. And we can use this exactly how you'd expect. So if we take our familiar pair of variables example and combine it with the addition example, this gives us a case which expects us to pass a tuple of integers, and we return an integer. Now that we've actually generated some cases, we can make some code using them. So here we have a match code generator, in which if we provide some code fragment of a scrutiny against which we compare the patterns to, or we compare against the patterns, and a list of the cases, we can then generate some result type based on performing that match. And this is used precisely as you'd expect. So if we provide it a particular scrutiny, here the tuple of 1 and 2, and our pattern which we've built up, we generate precisely the code you'd expect with matching the scrutiny on the values and producing the sum of them. Now, there's a few things to note in this. One is that the match combinator actually ensures the compatibility of the cases. So we require all the cases in the list to share both the input type and the return type. There's a few other things we need to take care of in this process, namely that we need to uniquely generate the names of the variables bound within the pattern. We need to uniquely generate the pattern variable names to ensure that we don't accidentally capture any scope, accidentally capture any variables from a higher scope. And we also need to take care in scope extrusion. So now we've introduced these bindings of R0 and R1. We need to ensure that they can't escape, possibly through some mutability like a reference. And for both of these second issues, we take the meta-OCaml approach, particularly the dynamic approach of detecting scope extrusion. Break for water. So at this point, we've very much achieved parity with meta-OCaml. in that we can build any patterns which we can statically define in advance. So what we want to do now is try and extend this to building the statically unknown patterns which we'd like. So in order to do this, we have two stages of this. We need to both build up the pattern itself arbitrarily, and we also need to build up the body on the fly. And we run into issues with both of these. So in the first case, it seems relatively simple that using our DSL, we might be able to build this up recursively. And in fact, we do run into an issue with this, which is namely the F-type in the pattern. So depending on the number of variables being bound in this list cons pattern family, we see that the F-type varies depending on a dynamic value. And so in order to actually be able to define this with recursion, we need to find some way to prevent this F-type from being leaked out. We also have the issue with generating pattern bodies in that we need some way in which we can generate expressions which potentially can handle an arbitrary amount of variables bound within a pattern. So we'll solve these issues in reverse order. So in order to generate pattern bodies, we introduce the idea of an inductive code definition. Now, an inductive code definition very much follows the structure of a classical inductive definition, so with a base case and a recursive case. So here, our base case for the list cons example, we provided the tail of the list, and what we want to generate from this is some code fragment as a return type. And for the inductive case, we pass in both the v, which is a newly bound variable within the pattern, and the accumulated body, which has been built up through this inductive definition. And on the right-hand side, we can define precisely how we incorporate this newly bound variable from the pattern into the overall body. And by repeatedly applying this, this inductive definition, we can build up a code fragment which uses arbitrarily many patterns. So here, for example, we're defining a sum of arbitrarily many values. Now, in order to solve the issue of exposing the F-type in patterns, we can use existential wrappers. Now, this is not as immediately simple as it seems, in that we run into a few issues with trying to define this, particularly around the opaqueness of the existential type. So because the existential type is completely opaque, it forces us to build up both our pattern and the body simultaneously to ensure that when we try and combine them with that arrow operator, they can in fact match, so as the existential types, although completely opaque, are the same. We also run into the issue of if we're trying to wrap and unwrap the body definition and imply inductive definitions, because of the opaqueness, we're not actually able to apply them. And so instead we need to use a continuation-based approach in which the effects of the inductive definition are encoded as continuations from our code to our code. And then we queue them up, compose them together, and then apply them a single time, which avoids the need to wrap and unwrap some value, which gets opaque. And so we end up with a wrapper of this type. So as you see, the F-type is no longer present on the outside, so we're shielding it as required. In this specific case for the list map example, we can restrict the pattern to be a list pattern of some number of conses. And you'll see the other thing we pass in is this idea of a continuation, which will produce our F, which is the body. From this definition of a wrapper, we can then define some combinators to generate statically unknown patterns. So in this example, we'll generate a n-cons pattern, so n variables cons together. And this can be done by passing in just a numerical value, a dynamic value, as in the number of cons cells to be built up. We pass in the base and inductive definitions, so we can generate the body we desire. And from the end of this, we'll get some case in a pattern matching expression, which accepts a list and gives us some result. Now, I won't go into full detail on this, but here is where our wrapper comes in. So we have some internal loop, which builds up both the pattern on the left by consing a var onto the existing pattern, but also building up the body on the right using the composition. And this is all wrapped so that the recursive call on the loop, the type remains the same, and we can actually define this. And once we're done with constructing this, we can simply extract out our pattern by pattern matching on the wrapper, pulling out the pattern and the continuation, retrieving the body by applying the continuation to an identity, and then constructing them with the arrow operation. So does this actually work in practice? Well, it does. So we can now define the list unrolling which we set out to in the first place. So we can define a function which is to generate an unrolled map for some arbitrary n integer, and we can set it up to generate a function and provide it a list of cases. And very much in following the structure of the original example, for the case of an empty list, we can provide an empty list. We can use our gen-n-cons combinator to build up the case for an arbitrary number of con cells. And here we see that in the base case, we simply fall back to the recursive call of the function we're generating. And in the inductive case, we're processing yet another con cell and tacking it onto the front of the body. And finally, we need to define the catch-all case for any lists shorter than the unrolling depth. And this does, in fact, work. So if we compare this map, a selection of different implementations of map functions in the green on the left versus a variety of unrollings, we see that not only does unrolling actually make it faster, which is useful for the motivation, but we also see that comparing both handwritten and generated versions of our functions, we see that the performance is roughly identical, and we can use something like this to determine that an unrolling depth of approximately 16 would be optimal in this case. So where does this leave us now? Well, what we have now is we have a type-safe way of generating arbitrary patterns, so both static and dynamic, and a broad class of bodies with this idea of an inductive code definition. And we also have a very extensible core system, so we can extend it both in terms of alternative pattern types, but also it's a very portable system, so it's applicable not just to OCaml, but also to other multi-stage programming systems, be they within the ML family, such as OCaml, or even outside, such as template Haskell. There is still plenty more that we're looking at, though. So in terms of implementing this into OCaml, the original work was built as a library on top of OCaml, and that leaves some caveats with detecting scope extrusion. So that's a work in progress to fix at the moment. But in the longer-term future, we're also looking at implementing some alternative pattern types. So while it's perhaps there are some very simple examples, so extending with string constant patterns would be very simple. There are a number of interesting problems to think about with alternative patterns, things such as GADT patterns, polymorphic variant patterns, and even things such as disjunctive patterns if we bind the variables in different orders within the disjuncts. And other things we're looking at are areas which we can apply this to, and this idea of building up patterns on the fly beyond just unrolling optimizations. So things such as potentially generating patterns on the fly for searching or querying. If you're interested in this and fancy reading more, I've got a whole host of links for you to look at. So the source code for this original implementation can be found at the first link on my GitHub. You can read the extended abstract, which is a 2-page format, or as I said, this was done as part of my master's dissertation. So if you want the full detail with quite a lot of commentary on different approaches and design choices and the kind of history of the techniques, you can find that there on my website. And there's also the work in progress implementation into OCaml, which I mentioned a few slides ago. Thank you very much for listening, and I'll be happy to take any questions.
Thank you for the fun talk. I wanted to ask about, at the end you mentioned thoughts about supporting more complex patterns in the future. And I was curious particularly about patterns, for example, involving record labels. And if you thought at all, not just about how to have patterns with record labels, or I guess the same thing applies to variant constructors, but how to abstract over the exact name of the label, if you know what I mean.
Yeah, so it's not something which I've looked into too much so far. It was very much, development's focused on the kind of core system without trying to get too creative with it. But yes, I think there is, record types are certainly something which we definitely look into. And I think the next step would probably be just data structure definitions in general and ADTs with custom names.
Thanks.
Hi, thanks for the talk. On your benchmarks, you showed there was a small gap between the generated definition and the handwritten definition. I guess what tricks remain in the handwritten definition that weren't generated?
So actually, the approach taken, the types, changed quite a lot from where we started in this. And the main reason for those changes was the generated code is designed to be as close to how you would handwrite it as possible. And that's actually what we've achieved. So the differences you see there are actually just random benchmarking differences. The code generated is nearly identical with one slight caveat, which I'm happy to talk about if you want. And while that made some parts of it more complex, it certainly aids in the readability of debugging these kind of things.
Okay, thank you.
Sorry, I missed the very end of your talk, so maybe this was answered, but wouldn't it be simpler to, instead of generating a curried function with all the pattern variables in a flat form, why not generate a nested structure like nested tuples so that it reflects the actual pattern shape, and you don't have to do this existential stuff, maybe?
Yeah. So, I think this one was quite nice in that there was both the simplicity of a flat structure and also there was there's some existing work on kind of first-class pattern representations as functions. There were a lot of contrasting ways, and actually, Jeremy and I had some interesting conversations with Matthew Pickering and he had a few different approaches, both in type-level ways of doing it and also tupled approaches. So there's lots of different ways. They each have their benefits. I haven't tried enough of them in any depth to comment of which ones are better and why.
I see. Yeah, it sounds like it would be a little bit simpler because you wouldn't need the intermediate type. You could just have 2 type arguments. And you wouldn't need this existential stuff, right? You don't need to flatten anything. You don't need to do some sort of type level computation because the pattern type just reflect its structure.
Yes,
okay.
I'd have to look at it.
Yeah. Okay, thanks.
So I have one additional question. Have you found during this work any use of it that you did not expect at the start?
So actually, that's one of the things I mentioned in the looking for more applications is that I very much got to the end of this. I never set out to do this in the first place. I set out to play with staging for optimizing data structures, and instead went, I can't do this. I wonder how difficult it is to solve this. It turns out it took a little while. And so I haven't looked too much beyond where else this can be applied. Actually, just a few days ago, I was thinking of this idea of being able to generate patterns on the fly is quite interesting for possibly things like searching or querying on the fly. But also, there's ideas around generating more interesting patterns. So patterns which we can't express in, say, OCaml natively, things like view patterns, or even things like can we union 2 patterns together or intersect 2 patterns together. This kind of work can be extended in that direction to allow us to do things which we never could with the base language.
Okay. Thank you. So the next speaker is remote, and I'm told there can be up to 5 minutes for preparation. So if things go well, it should be soon. So we'll wait for a bit.
Hello?
Okay. So if the remote presenter could turn on their camera and their slides so we can broadcast them.
To the slide. Can you hear me? So, I don't know if you can hear me. I can see a lot of echo passage. So I suppose that you can hear me and that there is a microphone in your room that should be. So should I start the presentation? I can also type messages on Discord if it can help. Yeah. Hello.
Do it in the room because it's gonna. Yeah, just tell them to turn off and on the screen share because we can't.
Oh, to the next presenter, please could you turn off and on your screen share because it's not currently working.
Okay. Background noise. I'm ready to start. If you can write a message on Discord or whatever, I'm ready.
Display it in person, very common, is then the presenter can't control the slides. They can't share their slides afterwards. We can't even load the it's more presenter, we have even just the slides. We can keep trying to work. I mean, unless you want to sort of
So there seems to be technical issues with the first presenter. So we have 2 remote talks, and so we'll try to get whichever talk that manages to broadcast first. So there may be a change in the schedule.
So for alpha, we have the projection on int equal to 1, so we have one int, 0t, so 0t, and one variable. T has no int, one int t, and the variable tau, and the gamma has an int and a variable tau. And the second equation, I will not go into much detail, but also generate the solution. This solution is valid only under this consideration, that's delta t equal int. And that's how we retrieve a solution for the ACE system. Okay, so really the core idea is because we split, we manage to reduce the number of solutions that we get, and also because we're not abstracting away subterms, so we have a better view of what we are trying to solve. If we come back to the example, then nothing has changed. The syntactic simplification is the same, the error problem didn't change, but now the ACE problem generates only 2 solutions. So this like massive blow up that we had, which was exponential in the number of constants in the second term, is completely stopped. So, and if we look at our table from before, so we had the full search, the index, and now with the shape, we see that the heavily polymorphic type query is also very, very fast. We have a 500 times speed up there. It's also speed up the search for the purpose some polymorphism. For the simple query, it was already fast and it not really improved anything there. Okay, so let's talk about the future of the tools. So we made dosing fast, so what's next? We know that it's starting to be usable, so to be useful for developers, we need to integrate it into the OCaml ecosystem. Also, we would like to expand it in 2 ways, so taking more type features from the OCaml type system, and also different axiom. For example, the unit types can be seen as neutral element for the project, so A times unit equal A. And we actually have already this implemented, but it's for another presentation. Make it even faster if you want to scale it to the full ecosystem. So far we are looking at developer ecosystem, but if we want to make it to the full ecosystem, we need to be even faster. And for that we have some ideas. So there are some symmetry in types that make that there is a lot of solutions, but solutions that are similar. And we want to cut down the search tree to avoid this solution by finding the invariant using graph automorphism. Then we would like to use a satisfy clone validation to faster backtracking. We already have a first step where we have an incremental way to build a solution for the ACE system. And also we could improve the index, which will just cut more indication out during the query. Thanks a lot for your attention, and I'm taking any questions.
So can you hear me?
Yes.
So thank you very much for this talk. One question that came to my mind is since you're considering currying, maybe we can look at not a strict match, but a closest match, or finding some type that is similar, but not exactly the same. Would that change the problem very much, or is it similar as a problem?
So it's depends a bit what you mean by similar. If you look at what we are doing, actually, if the query contains a unification variable in the argument, it can be used in particular with this like axiom that says unit is a neutral element for the product. As such, like as a wildcard saying that I want a function with this argument and maybe more, and arbitrarily more or not. So this will introduce some kind of like function which look like but are not exactly the same match. Now, if you're talking more about further searching, it's something that we would like to explore also, because it can be useful to indeed like make a query which is not complete. But we don't have a concrete idea on how to do that, especially in the formal setting with the unification.
So, thank you. So next speaker is Gabriel Scherer. And we are into the, we switched the second and the third talks of the session. So we are going into the second talk actually, and we are running about maybe 5 minutes late. And I'm waiting to hear that Gabriel is ready.
I'm ready, I think, if you can hear me.
So is it Gabriel that we are hearing?
Yes. Okay, so can you also see my slides?
All good, he should be able to hear you. The slides are just coming. They've all loaded this time.
Okay.
He's not going to share his camera.
And
it doesn't help. I'm on the Discord, and there is one red photo, which you can also write on the Discord.
So Gabriel, we don't hear you very much yet. We are going to turn up the volume.
Okay, I can also turn.
Okay, all good. So go ahead. So I'm introducing Gabriel Scherer from INRIA, the young person on the right that you are seeing here. And joint work with Thomas Refis and Nick Roberts. He's going to explain to us why OCaml multi-core and earlier version of OCaml are actually unsafe. So, Gabriel, is everything ready for you?
Yes, thank you. So I can go. As I said, I'm on the Discord, and I don't have any visual feedback on the room whatsoever. So if you want to ask a question during the talk, I don't think we can, or let me know if you can just write a message on the Discord. I asked some questions in your talks to go to the Discord. So, yes, joint work with Thomas and Nick. And Nick is at ICFP, maybe in the room, I don't know. So if you see him around, you can ask him a question. The talk is about OCaml in OCaml. Here is an individual example. So for the non-OCaml people in the room, I record the definition of option with a non or storm of A. Then we can define the type U. It is a record with a field A of type U, and a mutable field B of type int option. Now, if you are an SML person, a mutable field by just a field B of ref, and the same thing was the same issue. And so despite the function f on x of type U, you pick up the term from Q in domain, I will match on x, and if the field A is false, I return 0. The field B is none, I return 1. So at this point, we know that A is actually true, and B is actually some. And then the third clause has a when guard. And for those who don't know, when guard will check an arbitrary system. If it's true, it matches, otherwise it does not match. We'll look at what explains later. Then there is another if A is true and B on Y, return Y. But the when guard is vicious, very mutate, it's at none, and then it proves that the match was not matched. So the question is, what happens when you run this program? Okay? At this point, like B should be some, but in fact, you call the function, you need to go at this point, and you get a second. And this bug that, the ability to currently, so you could say, well, this is just when guards are bad, but you can also have function with, for example, annotation, to have the pattern matching, or databases, if you have a parallel language or complement, another. So there could be another thread modifying text at the same time. And you need an optimized. In this talk, I'm going to report the automata or backtracking displays approach to profiling pattern matching, describe the optimization in your OCaml compiler, and how we relax them. Okay, so pattern matching in the build we convenient to think of a value you mentioned n value at the same time shows us n patterns. How do you compile that away? Well, the naive idea to pick one column, so let's say the first one, the variable L here, and turn it into a case analysis on the head of the L. So I will generate, let's say, a function that say, well, if L is the empty list, and then I will simplify all my clauses with information. So I can drop the first column and have two of them. And if L is actually a non-empty list, I can simplify further because two of the clauses of the rows are incompatible. Because they are expecting the two, so I have only one row. As you can see, the clause bar is just repeated with this compilation strategy, and then the recursively find the matrix, and you may have other applications. So this is exponential and it's time. Okay, you don't want to have a program that generates a lot of megabytes of code and takes minutes to compile. So there are two approaches to avoid this price blow-up, which are well understood from the 80s and 90s. The first are the split-based algorithms that guarantee linear size of the generation at the cost of some repetition, some values we check it. Then you have the decimal, which use tuning or ad-hoc strategy to avoid the cost of the OCaml compiler base, and so are more meaning in a sense more open. If there is a corner case, it's probably better to become slower than to meet a lot of megabytes. The split-based algorithm splits this matrix of data in subgroups that can be combined without duplication. So typically, they are fixed. Typically, you will fix the boost of the first column, whether all the patterns start with a head constructor, or all the patterns have a wildcard. So if you do this in this case, for the case where you want close down, and you, on the other side, you generate some five that we try the first matrix, and if you don't do matrix, we spend will actually jump to one of the later ones, after you read the next one. And then you have the orange matrix, and then you trade. And once you do this, you can combine each map with sophisticated ones, and you get linear outside. But the inconvenience is that you read the check on the empty list, and you do it twice in the same time. Some execution. Okay, so what are the optimizations? The idea is in general, you have several matrices that for splitting. In the end, they split to a last match failure. And the OCaml compiler has to generate better. So, what are the notions involved? There is context. The context is the static knowledge that you have at this point in the matrix. That you achieve around the recursive compiling lower. From the context, you can use a jump summary. For a combined program, a jump summary is for each instruction some information about the context at the point of failure. At the source of the jump. And this lets you express the matrices that, for example, here, the matrix. And you want to get into the arrow coming from it. And if you do the context matrix one flame, you got an extra assumption that you can use for compilation of matrix. Maybe you know that what the replicator will be, or you know some ACDs that are. Then there is a default environment. What are the clauses that it contains? So if you know from the context that you have an empty list, and the next matrix does not actually match what you need, and you can skip this matrix and even the next which is what happened in this example, if you jump from one. And finally, you have total information. It comes from the type checker that tells you when maybe matching is topple, there is no value, and you can optimize that matching, not having a jump to the match checker. To summarize, the compilation function, totality information from the context, the context, the scoop matrix, and it returns the compiled matrix, the summary about all the states. And you can see if you start at the beginning, you have no information, you populate the default then you compile matrix 1, jump summary not of it, you use it, you get context to compile matrix 2, and so on and so forth. So, small room, the context, for example, in this example, we first discussion P, the true case, which we compare, the non-true case we are generating here, but it's the context, when the context is the first value is true, and the second one is not. So you can think of this as a pattern with wildcards, or this a pattern, or you can think of this as the general runtime value will be some tree, this point triangle, and we know a head prefix tree. The totality information, in this example, there is a match and fail. There is no fail. When that happens, the compiler is told that there will be no fail. But it does not need to branch or fixing the retrofigure. You can directly assume that N is generate a direct figure. The design of OCaml is a bit awkward. The design of the compiler is that checker totality, and also exhaustivity, left pattern control, emit nice running, and then it only give one zip to the pattern matching compiler. Instead of having the pattern matching compiler check that information as it. And at the beginning, people were very happy with this decoupled design, but as we added more features in our environment and JSPs, it is becoming a bit unpleasant. It should be better of the pattern matching compiler with type information. Okay, so back to the big picture. There is something about this that you don't understand, you are reaching out, right in the Discord after. So how do you relax with optimization? As a state, a reminder of the bug. We have two processes that are fine. There is David Wildcard and then Astro. The first bug, there are two problems. The first one is that the content, if you look at the split, there are two jumps, one and in the matrix 1 and 2. They both have the same content. A is true because we rule down the false case. B is some because we rule down the null. And the focus on the first one. At the time of the failure, but in presence of asynchronous on execution, when you get to the target, this may have been invalidated by a guard or by an operation or whatever. So actually, even use this refined context at the destination. So the solution is to erase any context information under a mutable position. If you do this, what you are. This is nice, this is good. The second problem is the pattern matrix. In this example, will not generate a fake matrix. Why is that? The checker believes that this how does the program totality because of the gap, but basically close the gap, remove the closing of the mapping, and in fact, without this closing, the better mapping will come, which in theory works whether the gap is true or false. But in this case, it was again the program is open, which is obviously in this case incorrect. So how do we solve that from the perspective of the mathematical compiler? The first idea is to forget about the type checker may be wrong, as an example. So maybe we just don't know. Sometimes the mathematical compiler will do context that plays a trade or is the code. You can use this information. Nothing from the type checker. The problem with that is that a lot of programs are going to generate both. In particular, when you have JDT, it's common to have an association where you only use a single and you do. In this case, you want the pattern matching direct access and not localize on that performance. You cannot use this technique. It's nice. So the second idea is to do it. I will forget the information. Only when I'm under a mutation, transiting, okay, we run to the return somewhere. The refine this idea again, the first step, which is the temporal reproduce, where we keep track of whether the submachine we compile is the first one, or is one that follows from the failure. So in this case, the one will be the first and the other are following. And if you know you are in the first, you know that you know pattern matching can run before you and jump. And so there are no interference. Any deduction you make affects the information of your current semantics. And you can trust it even under a multiple code. In particular, the case where the user has coverage tree as their code, there is no split. You can always do this without any splitting. And there will be only one pattern that has both temporal input and totality information. And in this case, the changes that we make will not directly at all. Even when the response we get information, this is the IPR. Okay, so we on a very basic less focus. And how do we set that to you? So one thing to say is we've seen an example of this bug. It's been launched in 2017 and now why is that? Because we believe that there is no buggy program in the world. So we have never found that suffered from this bug. Because not are exposed and they don't mutate the smoothly wide they are. So this is the bug that affects very program. But the fix minimizes more programs that would be slightly slower. Now, how do we combine the cost of one? So the reviewers of the were very basic. You should pick the compiler to write it. But in practice, people are not always focused. If there is no practice. So what we did is the case where we decimize the generated code due to the distrust of the totality information. And we compile the JSON code base again. And then what we reported, this was the last iteration. We found an issue in the world that had to be improved. Okay? But eventually, we had I tested the change, and indeed, it only flagged complex matches for mutable here. And in a code base with millions of lines of code, I found 3 instances, and it was possible to rewrite them without fault. Actually, I think that in those cases, probably the new code with more generation would have been fine after. You add a check somewhere. But if you are a user that is worried about performance, then you have to run your benchmark, that the change is fine and so on. It's a not forward. Whereas if you can just remind people to write the exact same intermediate implementation, you know that there are no, and it's much more relaxed. The warning actually is mistake by default. So most users like, hey, when we know one is not something like this, almost no one, and will not be good about it specifically. This is just fine. I'm done, and I'm willing to push. I can stop the room to ask.
Thanks for the talk, Benoît Montagu. If I remember correctly, there's a similar bug that involves what is called lazy patterns in OCaml. Were you able to also fix this issue with lazy patterns?
So I think some are proper way to introduce code execution. For a lazy value in the middle of pattern matching can cause this, basically the same issue, then you can explain it. And also
So, Gabriel, we have a bit of a sound issue. I think the last couple of sentences, we did not hear them well. Maybe we can try again?
yes, the short answer is that yes,
Okay, I guess your answer was mostly yes, so thanks.
Okay, so I'm sorry, Gabriel, for the sound issue. So I'll try just another question. I was wondering whether, so did multicore introduce new difficulties for this problem? New possibilities of unsound pattern matching compilations?
I can answer, if you want, I can also type an answer on Discord and you read it aloud, but you won't have echo problem, as you have.
Do you want to try to answer for him?
Sure. Or I can maybe. I think Gabriel was having some sound issues, so we weren't able to hear his full answer to the last two questions. But I reviewed his code, so I can say a few things, or at least a short or incomplete summary. The first question was about lazy patterns, whether the same unsoundness issue is also fixed for them. The short answer is yes. And then the question of whether multicore introduces new difficulties, and the answer to that is yes in the presence of, multicore is also addressed by the work here, but the introduced new issues, for, like, if this fix didn't exist, then there would be new issues in the face of data races where changes to mutable fields could then cause the same unsoundness that we saw earlier. Thanks.
So, thank you very much. Thank you, Gabriel.
least as funny as the other is. When you fly back to London? When did you fly back to London? Sunday. I'll try to fly to London. Sunday. I don't know what time. I think in the evening. Oh. I'm pretty sure mine's in the morning. Do you know which airport? United. Yeah, we're talking about We're supposed to do weather Sunday night, so I hope you make it home. It's supposed to be weather Sunday night? Oh, really? No weather? Well, I mean, I don't mind it. But your wife's with it, right? Yeah, we have to. Maybe do something. We've been walking around the road and then going in, but like, I mean, I mean, I think that's what the Sunday morning. And, must have been nice to you. Hey, so you know Richard's message about? Oh, do you know about that? Usually I say from the other city, particularly we've been on the number of segments from the research ones in the final next year. And like some other things, this year we've been a little bit about us every year, but also next year, so if you have other maybe about, I think that's something we should maybe. I don't know if you want to, but it should be fun.
Come on in. All right, good afternoon. We've made it to our last session of ML 2024, and I'm very happy to introduce you to work by my Jane Street colleagues, Chris Casingino and Ryan Choa. This was actually Ryan's intern project, which I think is pretty cool. And I'm not going to tell you what it is. I'm only going to tell you that I use it a lot and I like it very much.
Thanks very much, Jesse. Is working? Can you hear me? Yes. Okay. Sorry? Too quiet. Can you hear me? No? Can we get the...
Better? Switch it out.
Does that work? Can you hear me now? Yes, I'm getting thumbs up. Okay. All right. Yes, I'm going to talk about labeled tuples. This is a small feature we added to Jane Street's branch of the OCaml compiler, but I think there's a few interesting things to say about design choices and also comparisons to similar features in other languages like SML's flex records. So I don't know. I think it's fun to talk about a little bit. And as Jesse mentioned, this is work Ryan did on his intern project. Ryan actually just joined us full-time last week, so send your interns to come work with us. They can do fun things like this. Okay, label tuples. So let me start by explaining what this is. I mean, it is what it sounds like, but I'll show you a few examples to get started. Okay, this is a function that computes the sum and product of a list of integers. It does that by folding over the list and accumulating a pair containing the sum and product. And there's nothing that surprising here except there's labels on the tuple. So we define the initial value using a tuple that has labels on the two fields indicating which one is the sum and which one is the product. And then we fold over the list. And there's the function that we're folding over takes a labeled tuple as an argument and uses a pattern to get out the sum and product fields. That pattern is pun, just like a record pattern can be punned. And then we update the sum and product for the current element and return the new sum and product again using a pun. So what is the point of these labels? The point is to help you avoid errors, right? If you accidentally mixed up the order of the sum and product in the initial value relative to the folding function, you would get a static error. And similarly, if you mixed up the value of the arguments to the function in the tuple relative to the value returning, you would get a static error. So it just helps you keep track of which values are which in your program. So this example shows labeled tuple expressions in the initial value and the return of the function, and labeled tuple patterns in the argument of the function. There's also labeled tuple types, of course. This is what a labeled tuple type looks like. It looks like a tuple type. This is the type of the function f that's being folded here, and its argument and return are labeled tuples, and those look like tuple types but with labels. Okay, not rocket science. There are a few twists. We support a certain amount of reordering and partiality in pattern matches. So here I'm defining a labeled tuple, which is a pair of the integers x and y, called LT. This is an example from the OCaml top level. And then I want to get twice y. So I can do a partial pattern match on that LT and get out just the field named y by using the label. And then I multiply it by 2. And this works fine. This works as long as the compiler knows what the type is of the pattern that is being matched on. It needs that type information to do this kind of partial pattern match, because otherwise how do we know where the field y is in the record? So if the compiler doesn't know the type of the thing that's being pattern matched on, you're going to get an error like this. So in this case, I've written a function that tries to get y from something t that we don't know the type of. And so we try to do a partial pattern match on t, but the compiler doesn't know the whole type of the t tuple, so it gives you a static error saying, I don't know what the type of this pattern is. This may be surprising depending on which functional languages you're familiar with. I think it feels pretty at home in OCaml, where type information is used in a couple different ways in this kind of situation. It's used to do disambiguation of constructors, but more relevantly, it's used to make type checking of labeled function arguments nicer. And so this is pretty well at home among those kinds of features. Okay, a couple other features that we've added. Not every field in a tuple has to be labeled. So here I've got a triple. It's got, maybe I've computed the min, max, and average of some data structure. And I've chosen to label only 2 of the fields, the min and the max, because those 2 have the same type, and maybe I want to keep track of them. Whereas for the field that's a float, it's more obvious which one is the average. So this is supported. In fact, under the hood, the way we added this to the compiler is that all tuple fields just have optional labels. There's not separate labeled tuples and regular tuples. It's just every tuple field now optionally has a label. You can also repeat labels. So don't write a tuple that looks like this, but it is supported by the compiler. This is a 5 tuple, and it's got 3 fields labeled x, 1 field labeled y, and 1 unlabeled field. And then if you do a pattern match on it, so here I've done a pattern match where I get out the first two fields labeled x. So the way that works is I've written 2 fields named x, so that's going to get the first 2 out when it does the pattern match. And in this case, that's 1 and 3, so this sum adds up to 4. This may seem like, I don't know, a misfeature or something, but we think it's nice to have. You can imagine having a tuple where the things fall into 2 different categories, and you want to give label A to some of them and label B to some other ones. Also, it's analogous to labeled function arguments in OCaml, which, of course, you can have a repeated argument name. It's more necessary in the case of labeled function arguments to support currying, but I think this feature is very analogous to that feature in ways I'll talk more about later, and so it makes sense to have for this feature. Okay. So that's the feature. Hopefully it made sense. You may ask, why should we add this thing to OCaml? OCaml has a perfectly fine labeled product type. It's called records. What do we need labeled tuples for? So I think there's two reasons to add label tuples to the language. The first one is, OCaml has these labeled function arguments, and that's like a convenient way to, give a cheap name to parameters in your program. But there's a missing dual to that, which is like a cheap way to give the name to parts of values of your program. OCaml just doesn't have a thing to let you do that cheaply, and label tuples are that thing. And so in some sense, it feels like a missing dual to labeled function arguments. And many of the implementation choices I'm going to talk about later are motivated by that understanding. Also, like just from a practical perspective, people don't use records as much as they should. Sometimes when you're defining you've got three things, you need to return them from a function, and they're only going to be returned from this function and used in one other place. It feels like overkill to define a record, a new type for that one purpose, and so people don't. This is particularly true if your style guide says, oh, when you declare a type, you should add a printing function for that type, or maybe a serialization function. Maybe it should belong in its own module. Those kinds of things add burden to declaring new types, and so it can be nice to not have to declare a new type and just get some labels for free. So, of these two reasons, I would call the first one the primary reason we did this. It feels like a missing feature in the language once you start to think about it. But the second one is kind of more fun to talk about. So let me show you examples of some code that people write because they don't have label tuples. So here's one example. This is a function from the core Unix library, which is library Jane Street maintains, and it creates a new pipe, and it returns two file descriptors. Now, one of those is for writing, and one of them is for reading, and I'll let you make a mental guess about which one you think is which. But this is sad. In fact, the comment for this function doesn't even really make it super clear which one is which. So that's bad. They could declare a record that has two fields, one called read and one called write, and that would make it clear, but that felt like overkill to the author of this code, and so they didn't do that. And that's sad. So don't write code like that. Write code like this that makes it clear using a label tuple that the first one is for reading and the second one is for writing. Sad example number 2, polymorphic variant. So this is a thing people do kind of surprisingly a lot. This is an example pulled from Jane Street's code. So here, they're defining a tuple, and they've used polymorphic variant constructors to label the pieces of the tuple. They've got a price and a size, and they don't want to mix up how much something costs with how many of them they have. And so instead of constructing a tuple of price and a size, they've constructed a tuple of polymorphic variants containing a price and a size. This you can do. I personally think it looks a little ugly. It also begs questions like, okay, are these variants intended to have more constructors? What was the intent of this code? And also, there can be a dynamic cost. So if I get lucky, if this definition is very local in this file, and Jacques just gave me a shake of his head. If I'm lucky and this definition is very local in this file, then the compiler will eliminate these, do this unboxing for me. But these polymorphic variants do correspond to a box at runtime. And if, for example, I construct them by calling a function that doesn't get inlined, then this has a genuine runtime cost compared to the thing you should write instead using a labeled tuple, which has no runtime cost. Okay. Sad example number 3, you could build a whole PPX to get around this problem. So this is something somebody actually did inside Jane Street. They wrote a thing called PPX anonymous records. Now, a PPX is a preprocessor that's supported by the OCaml ecosystem. It's a source-to-source transformation. And they wanted essentially the equivalent of labeled tuples, so they built a PPX for that. So the way this works is this is the same example from the first slide, but using their PPX. This %anon thing, that's on line 2, that's an anonymous record expression, and the %anon question mark thing, that's an anonymous record pattern. And so you could do this. This has some downsides. I think it looks very ugly. Also, in the initial implementation, it had some runtime costs. They did eventually eliminate those. But lastly, using a PPX, it makes it less clear what code you're actually running because this is going to get transformed by some arbitrary program. And because it's a source-to-source transformation that doesn't have access to any type information, it can't do some of the things like partial pattern matches that we saw on the previous slides. So it's a worse feature in that sense. So don't do that. Write it using labeled tuples like we saw on the previous slide. Now, some of you may be thinking, OCaml already has a anonymous, a structurally typed product that you can just use in your programs, and that's the class system or the objects. So that's true. You could use objects to build a sort of cheap record where you label the fields of it, and you don't have to declare it ahead of time, so it eliminates that cost. I think in practice, the object system in OCaml is not super widely used. I don't have any examples to show you of people doing this in our code. Maybe some exist. People do occasionally use objects, but it's mainly when they want open recursion. That's the main use case we see for the object and class system. So you could use objects, but again, like the polymorphic variant example, and even more so, this is going to have a runtime cost relative to just using a tuple. Objects do have some overhead to do like lookup of the fields at runtime. And so that feels worse in a high-performance system. Okay, so don't do that. Use labeled tuples. So that's motivation. Let me now turn to talking about some of the design choices and some related work like flex records. So a choice that we made, and which I talked about earlier, is limited support for like reordering and partial matches. In particular, the compiler has to know the type of the thing that you're matching on in order to give you the nice behavior where the fields are reordered. And we could do something else. We could use row polymorphism to give these like really general types and just do inference that way. We didn't do that, and we think that's the right choice, and there's a few reasons why. The first reason, the obvious reason, is implementation complexity. This is a very small change to the OCaml type checker to add these labels, and like we got it done reasonably quickly and deployed it, and it's useful, and we don't have to add. I mean, OCaml of course has some infrastructure for row polymorphism because it's used in the type checking of polymorphic variants and the class system, but we don't want to add more of that. It adds a lot of complexity to the implementation. Also, that kind of implementation would probably come with some runtime overhead, like objects do. And we wanted these to have performance equivalent to tuples. And lastly, this version is more analogous to labeled function arguments, which, as I said, sometimes make use of type information to be type checked more conveniently. And I think that's really the main reason. We're really thinking about this as a value dual to what labeled function arguments give you for parameters. It's a small change. Yeah, that feels nice. There's a secret fourth reason, which is that if we make this too nice, people will use it too much. So like, OCaml does have records, and you can use records, and you should use records, right? You should declare, if you're going to have a type that's used by many parts of your interface, you should declare that type, give it a nice name, write down functions that do like printing and serialization, and we don't want people to stop using those types. Those are great. They should use those more. So by making this like, a cheap feature that has good behavior locally, but maybe is not as convenient as records globally, we encourage them to use records when that's appropriate. Okay. Also, one thing to say is, I think these choices are reasonable, in particular because this has proved to be very popular. So like, here's a message that we got sent on Slack shortly after shipping this. I feel very good about this. I've blocked out this person's name for privacy reasons. And ironically, they got the name of the feature wrong. It's labeled tuples, not named tuples, but that's fine. But people are generally excited about this. Not everybody was so easily convinced. Some people at the firm needed a little bit more convincing. But even the most stubborn folks came around eventually. And these are not the only sus messages we've received. It's very popular. It's used in thousands and thousands of files in our code base. I think it's gone over pretty well. Okay, so flex records. Surely there's some standard ML people in the room, and they're thinking, SML has this. What are you doing? Why is this interesting? And that's true. Labeled tuples are very much like SML's flex records. There are some differences. One difference is that we support these omitted labels and these repeated labels, which feel more natural in a tuple setting than a record setting. But I think the biggest difference is just that flex records are canonically ordered. So these two types in standard ML, which are records containing an integer y and an integer x and a Boolean y, in two different orders, are the same type in standard ML. And the way they get represented at runtime depends on the names of the fields. So they get sorted alphabetically, so the x is going to come first for both of these. And that's a choice you can make. We prefer to leave these as two different types, mainly because sometimes people write performance-sensitive code and they care about the memory layout of their programs. And so we want to give them the ability to express the memory layout that they want. And by making these two different types, we give them that ability. Also, I'm going to continue to say this version feels at home next to labeled function arguments, which also, like a function that has several parameters with the same names, the two function types are different if the order of the arguments are different. Okay, so I submitted this as an informed position talk. Maybe I should have some kind of position about this feature. And my position is not that this is like fundamentally better than flex records. I think it's extremely similar to flex records. They're both fine features. But my position is that a language like OCaml has room for both a structurally typed labeled product like these tuples or flex records, and a nominally typed labeled product like OCaml's declared records. I think these don't crowd each other out. It feels pretty natural when to use one or the other, and by making one of them tuples and one of them records, they kind of fit next to each other syntactically just fine. So my position is it's great to have both of these in your language. Okay. I want to take a divergent down some history. So after we realized we had basically just re-implemented flex records, I was like, oh, how did that end up in SML? What's the history there? As far as I can tell, there's no papers really just about flex records. But I did find these notes from 1985, written by Bob Harper at some SML meeting in Edinburgh. And these are like on the SML New Jersey website, and they're great. So one interesting thing about this meeting is that they were debating what to do about a labeled product, and they were debating whether to call it labeled tuples or flexible records. And at that time, they weren't really sure what to do, and in fact, they weren't really sure whether to include it in the language because they hadn't figured out how to do the type checking yet. I don't know what happens after this. I don't know like how flex records ended up in the language in the form they did. I would love to know that. If some of you know, I want to hear about it. But I think this is interesting history. And I would really recommend reading these notes. They're like 10 pages long. They are just a great read. You get a look into like how people were thinking about functional programming language design in 1985. Also, they're extremely relatable. If you've ever argued with anybody, about language design, I think you'll feel right at home reading these notes. Okay. Okay, to conclude, and I'm sure I'm way under time. Yes, to conclude, what else could we do with this? We haven't actually implemented projection for these. It's not super necessary because you can do the pattern match where you pull out one field. We could implement it. It's a little inconvenient syntactically because the most obvious syntax for projection is already used for records. So we could either use a worse syntax like .twiddle or something, although maybe that's used by OCaml, or we could make it type directed, which thing you're getting. Both of those feel kind of crappy, so we haven't done this yet. People haven't asked us for it that much. What people ask for all the time since we've shipped this feature, like once a week, is singleton labeled tuples. Like basically just the ability to add a label to an arbitrary value in their program. This surprised us a little bit, and also it's kind of hard to do just syntactically. Like if you've got f applied to twiddle x, is that f applied to the labeled argument x, or is it f applied to the unlabeled argument, which is a singleton labeled tuple? Now, that can be resolved with like parens somewhere, but it feels a little gross, and so we haven't done it. Also, like, okay, then if you continue down thinking about this, you might think, oh, well, actually, maybe I can just replace both labeled tuples and labeled function arguments with singleton labeled values and get rid of both of those features. But this doesn't work at all because labeled function arguments support like nice reordering and partial application in a way that these singleton labeled values would not make easy to do, at least as far as I see. So we haven't done that. One thing we are considering adding, though, is labeled function returns, which I think do most of the use cases that people want these singleton labeled values for and would feel right at home next to labeled function arguments, I think, in OCaml. Okay, I think that's everything I have. Thanks for listening.
Thanks for your talk and for the cool feature.
Sure.
If one of your design considerations was that you wanted tuple syntax to be similar to that for function parameters, was there anybody who really wanted question mark and equals and some of the other stuff?
Yeah, we have had some requests for optional tuple parameters. This doesn't feel, I'm not sure I see like a fundamental implementation obstacle, but I basically think, sorry, Jacques is sitting right there. I kind of think optional parameters are a misfeature, and I would remove them from the language. Although I love labeled function parameters, so I'm like not super inclined to build this. I think like there's a lot of bugs because of optional parameters, right? You forget to fill it in when you're supposed to, and I'm not inclined to give people that power more often. Does that make sense?
Absolutely. Thanks.
First question, since the named tuple are more structured, did you enable recursive types without rec types?
Did I enable recursive types? I didn't add any special support for recursive types. I think you can define a recursive type including a...
So if you didn't enable them, probably it's these are without rec types, because polymorphic variant and object support recursive type without the explicit option.
I think it just works, but I'm not actually sure. We could try it out later. I'm not sure what we'd implement it, to be honest with you.
Yes. Gabriel Scherer had a question online, and he was asking if he thinks that repeated labels are a missed feature. So he was wondering what happens if you disable the feature.
Sorry, I missed the last part of that. What happens if
you disable the option to have a repeated name?
Oh, nothing particularly bad happens. We don't have to have that. As I say, functions have this, right? So it feels natural. I'm not sure if it's used at all. This would be easy to find out. This would be a fun thing to find out. I don't know. One other reason that we wanted to have that is because, I mean, really under the hood, the unlabeled fields all share some unique label, right? Some unique anonymous label. And so, like, you can do a pattern match on a tuple where you just pull out the first anonymous field, and that works fine. And so they feel pretty analogous, if that makes sense.
Thanks.
Sure.
Hi, thanks for the nice talk. So maybe as a little bit of validation, it's interesting to point out that they're basically implementing the same thing in Scala right now. They're working on the same feature. In Scala, there are a lot of interesting things that come up, like which subtyping relations should these things have. And actually, this could be applicable to OCaml as well. Like, can you coerce a named tuple into an unnamed tuple? You could support that, right?
Could we support that? Yeah, that would work fine. I'm not sure I see a big. So OCaml, do you know about the no labels flag? OCaml has a flag that you can pass to it where, like, it just forgets all the labels. Like, we could make label tuples support that almost, except for the reordering and partial patterns, it would be hard. But a coercion to an unlabeled tuple should work fine. I mean, the labels are eliminated immediately after type checking in the translation to OCaml's lambda IR. So they're not doing anything. It would be easy to build a coercion. Yeah.
Right. So they should be able to support this sort of subtype coercions.
Yes.
Thanks.
Did you say that you could sometimes pattern match in a different order?
Yes.
But you also said that you don't want labels to commute. You want them to be different types. So I'm kind of confused with both assertions together.
Sure. So if the type checker knows the type of the pattern, then it can do the matching up for you. So if we know the type of the pattern, we just when you write the pattern, we like match up the fields with the way we know it's going to be laid out at runtime because we know the type of the pattern. This is very similar to the way function arguments.
I understand how you can do it, but when you say you don't want labels to commute, you want them to be different types because you don't want to have confusion.
Yes.
But now you say if I know the type and I put in different order, I say okay, it's okay. So.
But only in the pattern, right? We don't allow any reordering of expressions. So even if we know the type, you cannot reorder the expression. It feels a little convenient to us in the pattern, but maybe that's a mistake. I'm not sure.
So the other thing you said is that if you use flex records, they would not be as efficient.
No, I think flex records are equivalently efficient.
But I think if you put the same restrictions that when you don't know the types, you disallow them.
Yes,
it would be the same efficiency, I guess.
That's right. If I said that flex records are less efficient, then I misspoke. They're the same efficiency at runtime. So I'm sorry if I misspoke. Yeah. I think like objects would be less efficient. A version that used row polymorphism would be less efficient, which flex records don't use. All right, thank you.
All right, last up we have Jérôme Vuillon. He has been a longtime contributor to the OCaml and wider ML community. In particular, he put the O in OCaml and has built some other cool stuff, and now he's going to tell us about putting the OCaml on the web faster.
Okay, so I'm going to talk about my work on compiling OCaml to WebAssembly. I'm interested in running large programs in web browsers, and this has been possible for 16 years now, thanks to efficient JavaScript implementations. And an alternative to JavaScript is WebAssembly, which is also widely available. And if you want to run your favorite program written in your favorite favorite language, you can use a compiler. So now JavaScript is widely used. It's used everywhere, basically. And WebAssembly not so much. So I will start to explain why, and why I'm still interested in targeting WebAssembly. So WebAssembly provides a C-like environment. So you manipulate only scalar values, like integers and float values. And you can read and write values from a linear memory. And WebAssembly manages the stack so containing return addresses and local variables. So here is an example of WebAssembly module. You can import functions from other modules. So here it imports function square root that takes the float as argument and returns the float from another module math. And then it defines the function length that takes two parameters x and y, which are floats, and return a float. And this function stores the square of x and y into two variables, and then returns the square root of the sum of the variables. And this function is exported by the module. So a good thing about WASM is that it has a simple semantics. So compared to JavaScript, it has some much more predictable performances. And also from the implementer of the WASM engine, it's much easier to generate good code than with JavaScript. So JavaScript engines are doing some magic to generate efficient code, and sometimes the magic just does not work. And it's a very good target for C and C++ because the memory model is very similar. However, it's hard to use it for web programming because you cannot directly manipulate JavaScript values. You typically have to store them in some table and have an ID. And you have to manually release the values. And also, it's not very suitable for implementing, for supporting a GC-based language. And the main issue is that GC cannot see the local variables. So you basically have to spill all local variables to the linear memory whenever you allocate something or you call a function. And this can be costly. And also, it's a significant amount of work to implement this correctly and efficiently, minimizing spilling. And another issue is that now you have two GC, and they need to the GC of the language and the JavaScript GC, and now they have to cooperate somehow. And so this was the situation until recently. But now there is an extension of WASM with heap allocated values. And the heap is shared with JavaScript. And this is really a game changer because we no longer need to re-implement a GC. And it's possible to directly manipulate JavaScript values. And this extension is available at the moment in Chrome and Firefox, and very soon in Safari. So we can really use it now. So it adds reference types. At the top, there is any, so basically the type of all values, including JavaScript values. Then there is a type of value, type X of values with a physical equality. And then you have arrays, structs. And what is very interesting for OCaml is that you have integers in the same hierarchy. And for each type, you can specify whether it's nullable or not. And you can specify arrays using type definitions. So here, block is a mutable array containing values of type refec. And string is an array of bytes. And similarly, you can define struct by specifying their field. So a box float is going to be a structure with a single field that contains an unboxed value. So I'm now going to talk about my work. So starting point is JS OCaml, which I have implemented at the start, which is an industrial strength compiler, and it's a really popular way to run OCaml code on in web browsers. And it compiles OCaml bytecode to JavaScript, which turned out to be very convenient because it's easy to maintain. The bytecode is a fairly stable API. And it's easy to use because the user can just build a bytecode program and compile it to JS OCaml. It does not need to recompile all its libraries and build a specific environment for web programming. So the idea was to retarget JS OCaml to generate WebAssembly code instead. And I hope to get better performances and more consistent performances. And I wanted to minimize the chance that were needed to port the program from JS OCaml to OCaml. And I have a few demos. One is a Game Boy emulator. And you can see that it's not JavaScript code here. And I can run actually a really large program. And this is the Bsport website, which is a kind of social network for sport. And so you can keep track of all your sport events and things like that. And it's about 100,000 lines of code. And the pages are generated client side. And it just works with a few changes. I will come back to this later. So I'm going to talk about the implementation. So I reuse a lot of the JS OCaml code. So for instance, bytecode parsing and also all the optimization phases that works on an SSA intermediate code. And since WASM does not have closures, I added a closure conversion phase. And I actually implemented the way we generate structured code based on a very nice paper by Norman Ramsey at ICFP 2 years ago. And so the compiler is relying heavily on the Ben-Arian toolchain, which is a series of tools to manipulate WASM code. So WASM OCaml will generate some WASM text file, which is linked using WASM merge with the OCaml runtime. Then the code is optimized with WASM opt. And WASM beta DCE is used to perform dead code elimination. And I'm also using it to be able to know what JavaScript code needs to be linked together with the WASM code. I'm using a uniform representation of values. So all of OCaml values, that's really standard, all OCaml values as type refec. Integers as type are 31-bit integers of type ref if31. Constructors and tuples are represented as arrays with the first type, where the first field is an integer tag. So a block is an array of refec. A string is just a sequence of bytes, and the floats are boxed, as I showed previously. The operation of closures is quite standard as well. We need to be able to support clarification. So we have two entry points for the functions. If the number of arguments is right, then we can directly call the function. Otherwise, we pass the arguments one by one. And so closures will contain as a first field a one argument function for querying. And the second field is the actual call pointer, and then there is the environment. And that's an example which is a bit large, but well. That's a closure with for a function with two parameters and three values in the environment. So the first field is a function with one argument for querying. The second is a function with two arguments, which is the actual call pointer. And then the three last fields are the environment. And that's a subtype of all the function of with two arguments. And the code pointer, you can see that it takes actually a third argument, which is the closer, the environment, to be able to access the environment in the function. To implement the runtime, I need to provide an implementation for each primitives used in the current standard library. So that's the example here is for float addition. So for each function, so each primitive, I need to define a WASM function. And here the function will take two parameters x and y, unbox the float, add them, and then box back the float and return the result of the addition. Actually, this function is known by the compiler, and it will generate in that code, which allow more optimization by later on. And one sometimes needs to use JavaScript code, and I provide a way to link JavaScript code from WASM. So the WASM MetaDC tool can provide me a list of JavaScript primitives that are used in by the program, and then I reuse the JS4CAML linker to package these primitives. And so on the WASM side, I import the JavaScript function. And on the JavaScript side, I use a directive to name it, and so that JS4CAML knows what you need to use. I've implemented effect handlers in two ways, actually. One is inherited from JS4CAML, which supports effects by a partial CPS transformation. And it's simpler in WASM because WASM has tail calls, so you don't need to implement a trampoline to avoid exhausting the stack. And another approach is to use an extension, which proposal which is called JS Promise Integration, which allows to stop the execution when calling JavaScript to stop the current execution of the WASM program, to suspend the execution of the WASM program. And basically, the function will return a promise, and the WASM program will continue when the promise is resolved. And from JavaScript, you can resume another thread of execution of WASM, so you can switch between several threads, and that allows to implement effect handlers. And in the future, we plan to use the stack switching proposal, which provide the native WASM support for effects. There are some features that are not available in WASM, which are needed for implementing the OCaml runtime, and I have used JavaScript for that. So first, many mathematical functions are not available natively in WASM. So you can implement them in WASM, but it's simpler and probably faster to just import them from JavaScript. And the conversion between floats and strings are tricky to implement, and I'm just reusing the JavaScript implementation. WASM currently does not have weak pointers, so I'm using the weak and weak map classes from JavaScript to implement weak arrays and ephemerans. And for marshalling, I'm using the map object from JavaScript to deal with sharing. And I've ported the Varith Begint library to WASM. And for that, I'm reusing the JavaScript Begint. So for instance, for the addition of two Begint, the addition is implemented first in JavaScript. Then this function is imported in WebAssembly. And we implement the actual primitive in WebAssembly. And it's, so we cannot, because the type of OCaml values is refec, and the type of JavaScript values is ref_any, which is not a type of refec. I need to box the Begint, and so the WebAssembly function just unbox its arguments and box the result. So now I'm not going to talk about how we can interact with JavaScript from OCaml. So JavaScript values, as I've just said, are boxed. So it's just a structure that contains any value. And there are two functions, one to box value and one to unbox it. And these functions map 31-bit integers to ref E31. And the values of type refec are not actually boxed, which means that if you have an OCaml value, you can send it to JavaScript and get it back in still an OCaml value, not a boxed OCaml value. And then to implement then I need to implement a rather small number of primitives to be able to interact with JavaScript. And this primitive comes from are used to build the JSOCaml library. So for instance, you need to be able to access properties of an object, call functions and methods, and convert between JavaScript and OCaml values. So as an example, that's a conversion from JavaScript booleans to OCaml booleans. And so the funny thing is that in JavaScript, you can just use the identity function, because when you import this function, you explicitly give some types. and that is when you use it from WebAssembly, some conversions are performed. So the function toolbool take as argument any JavaScript value, so a Boolean, and return an integer. And the semantics is that it's to convert the JavaScript value into an integer. And for Boolean, it's just 0 and 1 or 1, and that's exactly what you want. And so the primitive is implemented by unboxing the JavaScript value, calling the conversion function, and then turning the integer into a 31-bit integer. And actually, several of these primitives are known by the compiler, and it generates better code. So, for instance, it avoids the string conversions for constant strings, and it can generate more efficient code for accessing properties and calling functions or methods. So in JSON OCaml, JavaScript objects are manipulated directly, and OCaml integers and floats are both mapped to JavaScript numbers. We don't make a difference. On the other hand, in case of OCaml, JavaScript objects are boxed. JavaScript integers are still mapped on OCaml integers when they fit, but usually they fit. And OCaml floats and JavaScript floats are really different. So it means that when porting existing applications, you need to explicitly conversion between JavaScript floats and OCaml floats. And also OCaml functions, they kind of worked when called from JavaScript, and that no longer work because they are implemented at WASM structures. So you have to, there was already a way to specify that the function was a callback, and now this is mandatory. And JS OCaml is a bit more picky. No, WASM OCaml is more picky because if you pass a null when an integer is expected, usually the program is going to trap. And also, there are some code that expect at least 32-bit integers that has to be changed. And in practice, it's not a lot of work. For instance, for the Bsport web app, I only had to change about 100 lines, and that was mostly adding some float conversions. And the process is relatively simple because your program either does not type, because some float conversions are missing, or just crashes because you have not added some conversions, or well, you're passing the wrong value from JavaScript to OCaml, something like that. But there was one case where we had problem where the code was wrong, was misbehaving, and it was not caught by the type checker, and usually the error was relatively silent. It was not crashing at the place where there was the error. That's physical equality, because JS OCaml is implemented using the OCaml physical equality. JS OCaml implements the OCaml physical equality using JavaScript strict equality operator. And this operator, when you compare two strings, for instance, they are considered as equal if they have the same contents. And with WASM physical equality, that's not the case. That's really it's really a physical equality comparison. So if you have two boxed JavaScript strings, they are not going to be equal. And what we have done is to not use directly refx, the physical equality, but when the two values are JavaScript values, we use the JavaScript strict equality. And that's relatively cheap because testing if something is of a given type is not very expensive. There is some Bloom support on the way. So I have made a PR on Dune, but it needs to be reviewed and accepted. So you can add some submodes to the JS OCaml directive to specify whether you want to generate JavaScript code or WASM code. Oh, and by the way, separate compilation is supported. And also I have added a way to specify some runtime WASM code to be added when compiling when generating some WASM code. I've made a number of benchmarks to evaluate the performance. And so on micro benchmarks, the results are pretty good. The running time is about 2/3 of the JavaScript running time. And the code is about twice slower than native code. And one exception is exceptions, which remain slow. So JavaScript exceptions are really, really slow. But WASM exceptions are much slower than usually OCaml in exceptions. So on these two examples, we are 2 to 3 times slower than bytecode, which is not great. And on large benchmark, it works pretty well. So if you compile the OCaml compiler itself, you get something which is twice faster than bytecode, which is not too bad. And for the Camel Boy example I gave previously, it's about 50% faster in WASM than in JavaScript. And in practice, it does not actually make much difference because most of the time is spent in writing the frame buffer, which is a typed array, and it's a bottleneck. Another benchmark I have used is a library for building interactive UI. And they have an implementation of table of numbers with a lot of small benchmarks. And so that GenStreet cares a lot about it because they want to display a lot of numbers rapidly. And again, the WebAssembly implementation is much faster than JavaScript. And using a native some native functions to convert between JavaScript and WASM between JavaScript strings and WASM array of bytes. It is actually twice faster. I have tried to evaluate a bit the cost of cast and boot check. That's possible because V8 makes it possible to skip checks. And we are doing a lot of cast and boot check. And so that's about 10% of the running time, which is not that good. 20% for the Bonsai library. Okay. Regarding file size, the generating WASM code is larger than JavaScript code. I think that's because the JavaScript is actually a really compact format, and I suspect that having to explicitly allocate closures takes some space. Regarding the CPS transformation for implementing effects, the effect on size is really low on JavaScript, which is actually yes, a bit surprising, but I think it's because the transformation is rather regular. And in WASM, it's a lot more costly because I think we have a lot more functions, so a lot more closure allocations to implement. However, the performance in JavaScript can be really low. So for Bonsai, it's 7 times slower after CPS transformation. And in WASM, there is less overhead. It's only about 70% slower. And I have tried to compare the two implementations of effects in WASM. And the one using the JS Promise Integration API is much slower because it's going through the JavaScript event loop each time it switches to a different stack. So rapidly, there's other implementation of other compilers from OCaml to WebAssembly. One of them is OCaml, which target core WASM and WASI instead, not web browsers. And they compile the whole OCaml interpreter to WASM using LLVM. And then they compile the bytecode to WASM. And they don't really rely on JavaScript except for exceptions. And OCaml is another compiler from OCaml to WebAssembly. It modifies the OCaml compiler, and it was really great because I think it's because of them that we have 31-bit integers in WASM-GC. But it's hard to compare the performance between their implementation and ours because it's only a prototype. And to conclude, OCaml supports the whole language. Most of the runtime is implemented. I have adapted a number of libraries and the build system. And it is used in production at Gen Street, and they seem pretty happy. And I plan to merge it back in with JS OCaml and make a release. So it's in progress. And then I would like to see whether I can optimize it a bit, avoid some casts and unnecessary boxing. It will be interesting also to support non-JavaScript hosts. Okay, so WASM OCaml is open source, and you can find it online. And I find that WASM-GC was very well designed. And it's surprising how well it works now already.
Thanks, Jerome. I think we have time for a question or two, for Dend.
So one thing I've encountered, like using this at Jane Street, is that sometimes like different primitives might have like slightly different behavior for like certain edge cases on like the C code versus the JavaScript code versus the WASM code. Like camel format float, for example, like does completely different things if you pass it like a format string that doesn't begin with a format specifier on the 3 platforms. So I'm wondering like if you've thought at all about how to like enforce consistency between the like implementations of primitives across the different backends.
So format floats should be about the same between, so maybe it's a bug. And we have a lot of small tests in just OCaml, and we are running it with one of OCaml as well to be able to compare the implementations.
Anyone else?
Yeah, I have one question maybe. So all your numbers were on V8 on Chrome, I suppose.
V8,
Your
right.
performance numbers. So of course, yeah, we know the exceptions are really depressing in performance on V8. Did you, by any chance, measure on any other engine, like how bad the exception overhead is?
Can you repeat?
Like you mentioned that exceptions are so slow, right? Like,
right.
And I suppose you're talking about also WebAssembly exceptions, like the exception proposal.
Yes, WebAssembly. JavaScript exceptions are really slow, and WebAssembly.
Right. But that was on V8. So did you measure that on some other browsers as well, like to compare it maybe? How
Not
bad it's
yet.
just V8?
I
Or?
tried Firefox at some point that it was even slower. So
Oh dear.
Maybe it has changed, but. And
Okay.
so, by the way, I made some changes in the V8 to make them faster. So.
Okay, that sounds good. Thanks.
So, but this is after my changes. So, initially it was about as slow as JavaScript.
All right. Thank you, Jerome. Thank you, everyone, for coming. We're done.